In the endless ocean of galaxies, most follow familiar patterns. But once in a while, the universe presents something that looks as though it should not exist. Hoag's object is one of those impossible sights, a perfect ring of glittering stars wrapped around a mysterious golden core with nothing but darkness in between. It looks less like a galaxy and more like a cosmic trick, a puzzle piece dropped from another universe. Astronomers have called it beautiful, haunting, even disturbing. Because if galaxies are supposed to obey the rules of structure, Hoag's object seems to have torn those rules apart. No one knows for certain how it formed. Was it a galactic collision frozen in time, a gravitational lens distorting the background, or something entirely new, a type of galaxy unlike any we have ever classified? Whatever the answer, Hoag's object challenges our understanding of how galaxies live and die. And before we dive in, let me ask you this. If you're watching from the very beginning, tell us in the comments where you are in the world right now and what time it is for you. You might be amazed at how many people are staring at the same cosmic mystery together across continents and across hours. Tonight we'll step closer to this enigmatic ring in the sky, and the deeper we look, the stranger the story becomes. When astronomer Arthur Hoag first spotted the object in 1950, he likely did not imagine that his name would become forever tied to one of the most extraordinary galaxies ever catalogued. On photographic plates it appeared as something odd, a round central glow surrounded by a ring of light. At first some wondered whether it was just an optical illusion, or perhaps a chance alignment of two separate galaxies along the same line of sight. But the more astronomers studied it, the more baffling it became. Through modern telescopes, Hoag's object reveals itself as a near-perfect circle. At its centre lies a compact golden spheroid of older stars, smooth and featureless. Encircling it at a great distance is a luminous ring filled with brilliant blue stars, some young and massive, burning hot and fast. Between the core and the ring stretches a vast dark void, empty space where in a normal galaxy one might expect spiral arms, dust lanes or scattered clusters. Instead there is only silence. This unusual architecture makes Hoag's object almost surreal. It does not fit neatly into the categories astronomers use. Spiral, elliptical or irregular, it is classified as a ring galaxy. But even among that rare class it stands apart. Most ring galaxies form from violent collisions, their structures messy and uneven, often showing tidal debris. Hoag's object, by contrast, is almost mathematical in its symmetry, as though drawn with a compass on the canvas of the cosmos. Its sheer size is staggering. The entire system spans about 120,000 light-years across slightly larger than our Milky Way. The outer ring alone measures about 75,000 light-years in diameter. Within that ring, countless blue supergiants blaze each several times the mass of our Sun, each living fast and dying young. These stars illuminate the ring like a necklace of fire suspended in the void. Astronomers have debated its origin for decades. Was the ring formed by a smaller galaxy plunging through the centre, compressing gas into a star-forming wave that expanded outward? Or is it the result of resonant gravitational instabilities sculpting gas into a circle around the core? Neither explanation is fully satisfying, and each observation seems to raise more questions than it answers. Even the apparent emptiness between the core and the ring is deceptive. Careful imaging reveals faint wisps of stars and gas hints of structure that could hold clues to its formation. The Hubble Space Telescope, with its sharp vision, has captured Hoag's object in exquisite detail, allowing us to see the contrast between the quiet golden heart and the blazing blue circumference. The image is one of the most striking ever taken of a galaxy, so much so that it often appears in astronomy textbooks and popular media as the archetype of a cosmic enigma. Looking at it, one cannot help but feel the pull of questions. Why is it so perfectly round? Why does it look so different from the chaotic, tangled galaxies that fill the universe? And if such a galaxy can exist, how many other forms might be out there waiting in the dark? Theories about the origin of Hoag's object have swirled for decades as astronomers attempt to reconcile its eerie perfection with the chaotic processes that usually shape galaxies. The simplest explanation is a galactic collision. Imagine a smaller galaxy plunging directly through the heart of a larger one. The gravitational shock would send ripples outward through clouds of gas, compressing them into a ring of star formation, much like a stone dropped into a cosmic pond. This bullseye collision model has been used to explain other ring galaxies, and computer simulations reproduce rings of hot blue stars expanding outward after impact. But Hoag's object resists easy classification. Most collision-borne rings are messy, their shapes irregular with debris trailing into intergalactic space. Hoag's object, by contrast, is astonishingly clean. The ring is not lopsided, not warped, not tangled with tidal streams. It appears as though some unseen artist carved a circle into the fabric of the universe with geometric precision. If a collision created it, the event must have been extraordinary, aligned with uncanny accuracy, and followed by billions of years of calm to preserve the symmetry. Another possibility is resonance. In spiral galaxies, gravity can set up oscillations that corral gas into rings. The Milky Way itself hosts a smaller ring-like feature called the outer Lindblad resonance, sculpted by the pull of its central bar. Perhaps Hoag's object is an extreme example where internal dynamics pushed nearly all the gas into a single vast circle, leaving the space between barren. Yet no simulations have convincingly reproduced such a stark separation between core and ring, making this hypothesis intriguing but incomplete. Some have suggested that Hoag's object may have formed through accretion, slowly drawing gas and stars from its surroundings into a ring over billions of years. But again, this does not easily explain the galaxy's extraordinary symmetry, nor why the central core is so detached from the outer rim. Theories multiply, yet each carries contradictions. The mystery deepens when we examine the core itself. Composed of older, redder stars, it resembles a modest elliptical galaxy, placed like a jewel inside the ring. Why would such an apparently isolated spheroid sit at the centre of a blazing blue halo? If a smaller galaxy passed through, why is there no sign of its remnants? Why is the central bulge so undisturbed? It looks less like a survivor of violence and more like a separate structure altogether. Astronomers turn to simulations, feeding equations into supercomputers to watch galaxies collide, merge and evolve. Across billions of years in fast-forward, they search for a match to Hoag's object, a digital twin that would reveal its origin. Some models come close, producing rings that echo its shape, but none capture its serene perfection. In every scenario, reality intrudes, distortions, warps, asymmetries. Hoag's object stands alone, a cosmic riddle that mocks our attempts at explanation. This is part of what makes it so captivating. Galaxies are not supposed to look like this. The universe prefers disorder, asymmetry, and perfection. Yet here is a galaxy that seems drawn by design as if order had momentarily triumphed over chaos. For scientists, it is both a frustration and an invitation, a reminder that the cosmos still harbours surprises we cannot yet explain. When the Hubble Space Telescope turned its sharp eye toward Hoag's object, the results were mesmerising. Hubble's cameras cut through the blur of Earth's atmosphere, revealing details invisible from the ground. For the first time, the symmetry of the galaxy could be appreciated in full clarity. The smooth golden core, the vast gulf of emptiness, and the dazzling blue ring of hot young stars. The image quickly became one of Hubble's most iconic portraits, splashed across textbooks, documentaries and astronomy websites as the very definition of a cosmic enigma. But it was not just beauty that Hubble captured. Within the central void, faint traces of starlight hinted at subtle structures bridging the core and the ring. Wisps of gas and tiny star clusters glimmered in the darkness, suggesting that the gulf was not entirely empty but sparsely populated. These delicate features are crucial clues hinting at processes that standard theories struggle to account for. Was the ring formed by shock waves propagating outward, leaving behind only faint remnants in the middle? Or is the space between simply in transition a quiet zone where star formation has ceased? Then came the detail that pushed Hoag's object from strange to almost uncanny. Peering through the telescope, astronomers noticed something nestled in the background just beyond the outer ring. Faint but unmistakable. Another ring galaxy appeared in miniature, perfectly framed by the circle of Hoag's object like a cosmic jewel within a jewel. The odds of such an alignment are vanishingly small. To have one rare ring galaxy in the universe is unlikely enough. To see another directly behind it centered within the view borders on the absurd. This chance alignment does not imply any physical connection. The background galaxy lies hundreds of millions of light years farther away, but its presence glimpsed through the cosmic window of Hoag's object feels like the universe winking at us, a reminder of how little we understand. To many who saw the image, it felt like staring into a cosmic illusion, a trick of geometry crafted on scales beyond comprehension. The Hubble portrait elevated Hoag's object from a curiosity to a symbol of the mysteries galaxies still hold. It became an emblem for the unexpected proof that even after centuries of mapping the skies, the universe can still surprise us with forms that seem to defy its own rules. For astronomers, it reinforced the importance of patient observation, because sometimes in the act of simply looking, the cosmos reveals something extraordinary. Yet the deeper the image was studied, the more questions piled up. Why was the ring so uniform in colour with stars of nearly the same age spread across tens of thousands of light years? Why did the central core remain so undisturbed, as if oblivious to the chaos that must have birthed the ring? And what story did that faint background ring whisper, framed so neatly within the foreground circle? Was it merely coincidence, or could it hint at deeper symmetries we have yet to grasp? For over a century, astronomers have used a simple diagram to classify galaxies. Known as the Hubble sequence, it arranges them into a familiar pattern. Ellipticals on one side, spirals with their graceful arms on the other, and irregulars filling in the margins. It is not just a taxonomy, but a framework for understanding galactic evolution, how galaxies might transform over cosmic time from one type to another. In this scheme, Hoag's object should fit somewhere, yet it refuses to cooperate. At first glance, its central core resembles an elliptical galaxy, smooth reddish filled with older stars that long ago exhausted their gas. Surrounding it, however, is not a spiral disk or chaotic halo, but a luminous ring of young blue suns. This combination does not sit comfortably anywhere in the diagram. It is as though two separate galaxies, one old and quiet, the other young and blazing, were stitched together into a single system, but without any signs of merging or disruption. This mismatch has unsettled astronomers. If the Hubble sequence is supposed to describe the life cycle of galaxies, where does Hoag's object belong? Is it a transitional stage, a fleeting structure that will eventually collapse into a more ordinary form? Or is it stable, an endpoint of evolution we had not anticipated? Theories falter because the galaxy seems to contradict the expectation that violent events leave visible scars. Here, if a collision created the ring, the scars have been erased with impossible precision. The puzzle grows deeper when we consider time. The stars in the outer ring appear to have formed roughly at the same epoch, suggesting a single burst of star formation that swept across tens of thousands of light years. To trigger such synchronized creation requires an enormous coherent event, the very sort of cataclysm that should leave chaos in its wake. Yet instead of chaos, we see symmetry. Instead of tidal tales, we see emptiness. It is as if the galaxy experienced violence without trauma, order without disorder. Some researchers have suggested that perhaps our categories themselves are too rigid. The Hubble sequence, after all, was designed in the 1920s, long before astronomers could see galaxies in such detail or simulate their formation on supercomputers. It may be that Hoag's object is not an exception, but a signpost pointing toward a broader diversity of galactic forms. Perhaps galaxies are not confined to neat boxes, but can follow stranger evolutionary paths shaped by rare alignments or unusual environments. And that possibility forces us to confront an uncomfortable truth. If our own classification schemes fail here, how many other galaxies are we misunderstanding? What structures might lie hidden, dismissed as anomalies because they do not conform to our diagrams? The deeper we look, the clearer it becomes that Hoag's object is not just a curiosity. It is a challenge, one that shakes the foundations of how we think about galactic life cycles. The Hubble sequence remains a powerful tool, but perhaps it is incomplete. Perhaps the universe is whispering through Hoag's object that its creativity exceeds our categories. The question is not only how this galaxy formed, but what it tells us about the limits of our imagination, and whether we are prepared to redraw the very maps by which we chart the cosmos. If Hoag's object were the only ring galaxy in existence, it might be easier to dismiss it as a one-off curiosity. But the universe contains other ring galaxies scattered across the deep sky. They are rare, only a fraction of a percent of all known galaxies, but they do exist. Some are clearly the aftermath of collisions, their rings expanding outward like ripples in water, jagged and distorted by gravitational violence. The Cartwheel Galaxy, for instance, is a spectacular example. A huge wheel-like structure formed when a smaller galaxy plunged straight through its center, triggering a circular wave of star formation. Its ring glows with bright blue knots where clusters of hot stars are being born, while its interior remains chaotic, littered with dust lanes and tidal debris. Yet when placed side by side with Hoag's object, the differences are striking. The cartwheel and others like it are messy, scarred by their violent births. Their rings are uneven, their cores disturbed. Hoag's object, in contrast, looks serene. Its ring is smooth, almost mathematical in precision, with no obvious signs of the turbulence that usually accompanies such structures. It is as if Hoag's object exists in a separate category, not just another ring galaxy, but something altogether different. Other candidates, such as polar ring galaxies, add further complexity. In these, a ring of stars and gas orbits perpendicular to the host galaxy, forming a striking cross-like structure. These polar rings are thought to form when material is captured from a passing galaxy and settles into a stable orbit around the host. They are fascinating in their own right, but again, they look nothing like Hoag's object. The geometry is different, the dynamics more easily explained. Hoag's object remains stubbornly singular, a structure that fits no known mould. The rarity of such galaxies raises another question. Is Hoag's object truly unique, or have we simply not looked hard enough? The observable universe is vast, and our surveys, though expanding rapidly, still cover only a fraction of the sky, with the depth required to detect such unusual forms. It may be that hidden among the billions of galaxies are other near-perfect rings waiting to be revealed by telescopes of the next generation. If so, Hoag's object could be less of an anomaly, and more of a clue evidence of a class of galaxies we're only beginning to glimpse. This possibility excites astronomers because it shifts the conversation from how could this one galaxy exist, to what physical processes create these rings and under what conditions. If Hoag's object is not unique, then its mystery transforms into a broader challenge, to map out the circumstances that give rise to perfect rings and to place them within the larger story of cosmic evolution. But until more are found, Hoag's object remains an outlier, a solitary beacon of symmetry in a universe that usually prefers chaos. The search for analogues continues with sky surveys like the Sloan Digital Sky Survey and upcoming instruments like the Vera Rubin Observatory, scanning deeper and wider than ever before. Each new dataset is sifted for rare shapes, the oddities that defy classification. Somewhere out there, perhaps another Hoag's object waits its perfect ring glimmering in the dark. And if we find it, the questions may only multiply. Is it coincidence, or is the universe telling us that what we see as anomalies are in fact part of a larger hidden pattern? If the mystery of Hoag's object has endured for more than 70 years, it is partly because our tools for studying it have been limited. Even with Hubble's sharp vision, the galaxy remains a distant blur of unresolved stars. To peel back its layers requires instruments capable of probing deeper, wider, and across wavelengths invisible to the human eye. And now, with a new generation of observatories, astronomers stand on the threshold of insights that could finally shift the debate. The James Webb Space Telescope offers one of the most promising avenues. With its infrared eyes, Webb can see through dust and capture the faint glow of older, cooler stars that Hubble cannot. Pointed at Hoag's object, Webb could reveal the subtle structures in the void between the core and the ring, exposing whether faint streams of stars connect them, or whether the separation is truly stark. It could also analyse the light of the ring's blue giants, measuring their chemical abundances to determine how and when they formed. Were they triggered by a single shockwave billions of years ago, or are they the result of a slower, more drawn-out process? Webb's spectroscopic instruments can dissect starlight into its components, turning each photon into a clue about the galaxy's history. Meanwhile, the Vera Rubin Observatory, with its legacy survey of space and time, will map the sky in unprecedented detail over a decade-long campaign. Rubin will not only capture millions of galaxies, but track their changes over time, identifying transient phenomena and subtle variations in brightness. In that colossal data set, astronomers may discover other galaxies resembling Hoag's object, perhaps rarer examples of perfect rings or systems caught in the act of forming one. If Hoag's object is not alone, Rubin is our best chance of proving it. Other observatories add complementary perspectives. The Atacama Large Millimeter Array in Chile, sensitive to radio waves emitted by cold gas, could map the distribution of hydrogen in and around Hoag's object. Such maps would show whether gas is flowing inward-outward or circulating in patterns that could hint at the galaxy's formation. X-ray telescopes could search for signs of past collisions such as hot gas left behind in the wake of a plunging intruder. Each wavelength of light adds a layer of truth, and together they weave a more complete picture. The challenge, of course, is distance. Hoag's object lies about 600 million light-years away, far beyond the range where individual stars can be resolved except for the brightest giants. We cannot study it with the intimacy we give the Milky Way or Andromeda, yet with the sensitivity of Webb-Rubin and ALMA combined, we can extract patterns, motions and histories encoded in its light. Each observation becomes a test of the theories, a way to narrow down the possibilities. And there is another tantalizing angle: gravitational lensing. The bending of light by mass sometimes allows background galaxies to be magnified by foreground objects. Could Hoag's object itself serve as a natural lens, amplifying hidden structures in the depths of space? Or could a careful analysis of its shape and ring reveal the influence of dark matter sculpting it into form? These questions tie the fate of one peculiar galaxy to the fabric of cosmology itself. As technology advances, Hoag's object will no longer be a static curiosity frozen on a photographic plate. It will become a dynamic test case probed across the spectrum, dissected by algorithms, and modelled by simulations running on the world's most powerful computers. And perhaps finally we will step closer to understanding how a galaxy that looks like no other came to be. One of the strangest features of Hoag's object lies in the relationship between its core and its ring. In most galaxies with ring-like structures, the central region is active, filled with gas dust and ongoing star formation. But the core of Hoag's object is old and quiescent, a spheroid of ancient stars with little evidence of recent activity. Surrounding it, the ring blazes with massive short-lived blue stars that could not have existed for long. This juxtaposition raises an unsettling question. How can two regions of the same galaxy exist in such radically different states? Spectroscopic studies show that the ring stars are relatively young, only a few 100 million years old at most, while the core is many billions of years old. That implies a sudden, relatively recent burst of star formation confined to the outer rim. What triggered such a burst? If a smaller galaxy passed through its impact, could have sent waves of compression outward, igniting the ring. But in that case, where is the intruder? Surveys of the surrounding sky reveal no clear culprit, no nearby galaxy with the right mass or trajectory to explain the event. The collision model remains plausible, but the evidence is missing. Adding to the puzzle is the sharp boundary of the ring itself. Most star-forming regions grade gradually into surrounding space, with density thinning over distance. In Hoag's object, the ring appears almost cut off, like a defined edge rather than a gradient. Stars within the ring show similar ages, suggesting they formed nearly simultaneously. Yet the mechanism that could coordinate star formation across 75,000 light-years with such precision remains unclear. Radio observations add another layer. Neutral hydrogen gas, the raw material for star formation, is concentrated in the ring and sparse in the core. This distribution supports the idea that a violent event swept gas outward and left the center depleted. But even this does not explain why the ring remained so undisturbed, maintaining perfect symmetry, rather than fragmenting into arcs and clumps as seen in other collision rings. The uniformity is itself a mystery. Another enigma comes from the faint structures glimpsed in the gap between core and ring. Deep imaging has revealed traces of stellar streams barely perceptible against the dark. Some astronomers suggest these may be remnants of disrupted material, the ghostly signatures of a past interaction. If true, they could be the forensic evidence of the galaxy's creation. Yet the streams are so faint and ambiguous that their interpretation is debated. Are they genuine features of Hoag's object or background noise in the imaging process? Only deeper exposures can settle the question. The background galaxy framed inside Hoag's object adds an almost mocking twist. That second ring galaxy, perfectly aligned, reminds astronomers that chance alignments can create illusions. Could Hoag's object itself be an illusion, not a single coherent galaxy, but two superimposed structures along our line of sight? Detailed spectroscopy argues against this, showing that the core and ring share the same redshift, the same cosmic distance. They are truly part of one system. But the alignment of another ring galaxy in the background makes some researchers wonder how often such accidents might fool us. And then there is the question of stability. Will the ring persist for billions of years, or will it gradually dissolve back into a more typical disk? Simulations suggest that rings formed by collisions expand and fade. Over time, their brilliant blue stars dying out, leaving behind only faint remnants. If so, Hoag's object may be temporary, caught in a rare moment of symmetry before entropy reasserts itself. But if the ring endures supported by hidden dynamics, we do not yet understand then it represents a stable configuration unrecognized in current models. For now, the galaxy remains suspended between hypotheses, each with evidence but none conclusive. Every new observation seems to answer one question while raising two more. To unravel Hoag's object, astronomers have turned to dynamics, the study of how stars and gas move under gravity. In a typical galaxy, motion reveals structure. Spiral arms, bars, and disks all leave signatures in the rotation of stars and the distribution of gas. If Hoag's object is the product of a collision or resonance, its internal motion should bear the scars. But once again, the data refuse to tell a simple story. Spectroscopic measurements of the ring show that stars are rotating around the core at speeds of roughly 200 kilometers per second. This is consistent with the rotation curves of large galaxies, where velocities remain high even at great distances from the center. Such curves are one of the classic indicators of dark matter. Without an unseen halo of mass, the stars would not have enough gravity to hold their orbits. Hoag's object, it seems, is no exception. Its ring would fly apart without a massive dark matter envelope binding it together. Yet the distribution of those velocities is strikingly smooth. In galaxies shaped by collisions, astronomers often detect asymmetries. Stars moving faster on one side than the other, or irregular flows of gas that betray turbulence. Hoag's object, in contrast, shows remarkable uniformity. The ring appears dynamically stable, with little evidence of the chaos expected from a violent origin. This stability deepens the mystery. Did the galaxy somehow settle into equilibrium far faster than models predict? Or was its formation gentler than we imagine, leaving behind little in the way of kinematic scars? Gas dynamics provide another clue. Observations of neutral hydrogen indicate that the gas in the ring orbits coherently with the stars, forming a single rotating structure. In most collision rings, gas flows outward in expanding waves, gradually dispersing into the intergalactic medium. Here the gas seems to have organized itself into a settled, long-lived disk. If this is the case, Hoag's object may not be a fleeting anomaly, but a stable configuration, one that challenges our understanding of galactic morphology. But questions multiply. Why is the central core so detached from the rotation of the ring? Its older stars show little evidence of motion linked to the outer structure, almost as though the two components are separate galaxies stitched together by gravity. If they truly formed from a single event, their motion should be more entangled. The decoupling between core and ring raises the possibility that the core is a relic of one galaxy, while the ring was built from material of another, yet there are no obvious remnants of such a merger. Dark matter complicates the picture further. If the halo around Hoag's object is unusually massive or unusually shaped, it might have guided gas into a ring and stabilized it against collapse. But mapping the dark matter distribution requires detailed gravitational lensing or extended rotation curves beyond the ring data we do not yet possess. Without them, the true role of dark matter in sculpting this perfect circle remains speculative. Astronomers continue to refine their measurements, using ever more sensitive spectrographs to tease out tiny velocity differences across the ring. So far, the picture remains consistent. Rotation is smooth, stability is high, turbulence is low. Each result pushes Hoag's object further away from the messy collision models and closer to something altogether stranger, a galaxy that defies our expectations not only in appearance, but in motion itself. And if its dynamics are stable, then the next question becomes even more perplexing. How long can such a perfect ring survive in a universe where disorder usually wins? If dynamics describe how Hoag's object moves, the chemistry of its stars tells us how it grew. By breaking down the light into spectra, astronomers can measure not only velocity but also metallicity, the abundance of elements heavier than helium forged in earlier generations of stars. These chemical fingerprints are crucial because they reveal the history of star formation and the lineage of material from which new stars arise. In the core of Hoag's object, the stars are old and metal-rich, resembling those in elliptical galaxies. This indicates that the central region experienced intense star formation billions of years ago, quickly enriching its gas with heavy elements before running out of fuel. The result is a spheroid of aging stars, reddish in colour with little evidence of new birth. The story of the core is a familiar one: rapid formation, exhaustion, and quiet senescence. The ring, however, tells a different tale. Spectroscopic studies reveal lower metallicity in its brilliant blue stars, suggesting that they formed from relatively pristine gas, less enriched by previous generations. This implies that the gas forming the ring may not have come from the core itself, but from an external source, perhaps accreted from the intergalactic medium, or stripped from another galaxy. The youth of these stars, only a few 100 million years old, contrasts sharply with the ancient billions of the core. It is as though two epochs of galactic history are playing out side by side. This duality raises fundamental questions. If the ring's gas originated externally, where did it come from? Deep surveys of the surrounding region show no obvious donor galaxy, no tidal tails, no clouds of debris that could account for the material. If it came from the intergalactic medium, why did it settle into such a perfectly symmetric ring instead of a chaotic disk? The absence of clear evidence leaves astronomers speculating, piecing together possibilities that all seem incomplete. Another enigma lies in the uniformity of the ring stars. In most galaxies, star formation occurs in waves with clusters of different ages scattered across the disk. In Hoag's object, the stars of the ring appear almost coeval, born nearly at the same time. This suggests a single triggering event rather than continuous formation. But if so, what event could synchronize star birth across 75,000 light-years with such precision? The timescales alone make it difficult to explain. Even shock waves from a collision would be expected to introduce irregularities, yet here the pattern is smooth. Comparisons with other galaxies deepen the puzzle. In the Cartwheel Galaxy, the outer ring is full of clumps, each representing a starburst ignited at slightly different times. In Hoag's object, the clumps are subdued, the distribution smoother. The metallicity differences between ring and core are also sharper, suggesting less mixing of material than expected. The system behaves as though two galaxies were overlaid but never blended. These chemical and age contrasts reinforce the idea that Hoag's object is not just a rare morphology, but a hybrid of histories. The old metal-rich spheroid sits untouched, while the young metal-poor ring burns brightly around it. The two components coexist, but seem to belong to different stories stitched together by gravity into a single structure that should not exist. For astronomers, this mismatch is both frustrating and tantalizing. If we could explain the origin of the ring's gas, the timing of its starburst, and the uniformity of its metallicity, we would move closer to solving the enigma. Instead, each observation seems to complicate the picture, further revealing a galaxy that is not merely unusual but actively contradictory. In the modern era of astrophysics, computer simulations have become one of the most powerful tools for understanding galaxies. By encoding the laws of physics into supercomputers and allowing billions of virtual years to unfold, astronomers can watch galaxies form, collide, and evolve in fast-forward. Projects like Illustra's Eagle and TNG 50 have produced vast digital universes containing thousands of galaxies, many of which resemble the spirals and ellipticals we see through telescopes. These simulations reproduce large-scale structures, star formation rates, and even the cosmic web of dark matter filaments. Yet amid all their successes, they have failed to produce a convincing analogue of Hoag's object. In illustrious ring galaxies do appear, but they are typically the messy aftermath of collisions. Their rings are warped, irregular, and studded with clumps of new stars. None show the clean geometry of Hoag's object. In Eagle polar ring galaxies emerge in some runs where streams of gas are captured into stable orbits around existing galaxies. These are striking, but again the structures differ sharply from Hoag's perfect circle, enclosing an isolated core. The absence of a Hoag's twin in simulations is telling. If such galaxies are possible under standard physics, they should occasionally emerge in these massive datasets. Their rarity in models suggests that the processes producing Hoag's object are either extremely uncommon or not well captured by our current prescriptions of star formation gas dynamics and feedback. For instance, simulations often struggle to model turbulent magnetic fields, or the fine details of gas cooling, all of which may be critical in shaping unusual morphologies. Attempts to deliberately reproduce Hoag's object in targeted simulations have met with partial success. By carefully engineering a collision scenario, researchers can generate rings of stars surrounding older cores, but the results always carry imperfections. Asymmetries, tidal tails, disrupted centers. The simulations never quite match the serene symmetry seen in the real galaxy. It is like trying to sculpt a perfect circle in water. Theory allows it, but practice produces ripples. This disconnect highlights the limits of even our most advanced models. Simulations are built on assumptions: how gas behaves at small scales, how stars inject energy back into their surroundings, how dark matter interacts with visible matter. Tiny errors in these assumptions propagate into large-scale outcomes. If Hoag's object cannot be reproduced, perhaps it's exposing gaps in our understanding of how galaxies grow and organize themselves. One particularly stubborn issue is the synchronization of star formation in the ring. In simulations, even when a ring forms, starbursts are staggered with clusters igniting at different times. Achieving a uniform, nearly so-evil population across tens of thousands of light-years requires conditions the codes rarely produce. Was there some finely tuned trigger in Hoag's past, or is our modelling of feedback and gas collapse too simplistic? The challenge now is twofold: to refine simulations with better physics and to search the universe for more examples. If Hoag's object is truly unique, simulations may never replicate it without special conditions. But if others exist, then our models must evolve to account for them. Either outcome carries weight, a single anomaly demanding explanation, or a hidden population waiting to be revealed. For now, the galaxy remains absent from our digital universes. It exists only in reality, suspended in the darkness 600 million light-years away, daring our simulations to catch up. To crack the mystery of Hoag's object, astronomers know that no single telescope or wavelength can provide the full picture. Each type of light reveals different aspects of galactic anatomy. Optical imaging shows the stars themselves. Infrared unveils cooler dust-shrouded regions. Radio waves trace the hydrogen gas that fuels star formation. X-rays expose hot plasma and violent events. Put together, they create a layered portrait of a galaxy's history and structure. In the optical, Hubble has already delivered the most iconic view, capturing the golden spheroid core and the blazing blue ring in exquisite detail. But optical light alone leaves gaps. It cannot easily distinguish faint streams of gas in the dark gulf, nor penetrate dusty regions that may hide critical clues. That is where the James Webb Space Telescope steps in. Its infrared instruments can peer through dust and measure the faint glow of older stars within the ring, potentially revealing whether hidden populations bridge the gap between core and halo. Webb's spectrographs can also dissect the chemical fingerprints of the ring's stars, comparing them to the metallicity of the core with unprecedented precision. On the radio front, the Atacama Large Millimeter Array has the power to map cold hydrogen and molecular gas in and around Hoag's object. Such maps are essential for testing collision theories. If the gas is flowing outward in coherent shells, it would support the idea of a past impact. If it is rotating smoothly with the stars, it suggests a long-lived stable configuration. Either result would narrow the possibilities. Radio observations could also search for faint gas streams beyond the ring, the telltale debris of a vanished intruder galaxy. X-ray telescopes bring yet another angle. Collisions and mergers often leave behind hot gas clouds heated to millions of degrees and glowing in high-energy light. If Hoag's object is the relic of such a cataclysm, subtle X-ray emission might linger in its halo. So far, no strong X-ray signals have been detected, but deeper surveys are needed to be sure. The absence of X-rays would weigh against the collision model, while their presence would provide a smoking gun. Even gravitational lensing has a role. If the dark matter halo of Hoag's object is particularly massive, it could bend the light of background galaxies, distorting them into arcs or subtle shears. Careful measurements of these distortions could map the dark matter distribution, testing whether an unusual halo shape contributed to the formation of the ring, though the effect would be faint. Upcoming surveys like those from the Vera Rubin Observatory could provide the statistical depth needed to detect it. Coordinating these efforts is a challenge in itself. Each telescope operates in a different domain, requiring proposals, observing time, and careful data integration. But step by step, the multi-wavelength campaign builds a dossier on Hoag's object. Every dataset adds a clue. The smooth rotation of stars, the metallicity contrast between ring and core, the presence or absence of hot gas, the shape of the dark matter halo. Piece by piece, astronomers assemble the puzzle, hoping that somewhere in the overlap of these perspectives lies the answer. The irony is that while Hoag's object appears deceptively simple in photographs, just a golden sphere encircled by a blue ring, its reality demands the most complex observational strategies we possess. What looks like symmetry on the surface hides layer upon layer of unresolved detail, and the deeper we probe, the more intricate the mystery becomes. Astronomers often speak of galactic archaeology, the effort to reconstruct a galaxy's past from the faint traces left behind. In the Milky Way, this means mapping stellar streams from long-digested dwarf galaxies. In Hoag's object, it means scrutinizing every faint smear of light within and around the ring to search for clues of a forgotten event. These traces are the fingerprints of history, subtle but telling. Deep imaging has already revealed hints of faint stellar material in the gulf between the core and the ring. These strands are barely visible, their brightness close to the limits of detection. Some astronomers interpret them as remnants of disrupted gas clouds or tidal streams lingering after an intruder galaxy tore through. If true, they would serve as forensic evidence of a cataclysm now largely erased. But the evidence is ambiguous. Distinguishing a genuine feature from background galaxies or random noise requires deeper exposures and painstaking analysis. For now, the case remains open. Another potential clue lies in the orbits of individual star clusters within the ring. Precise measurements of their velocities can reveal whether they are expanding outward, as in the aftermath of a collision, or orbiting in settled paths like a long-lived disk. Early data suggest rotation dominates, but the precision is not yet sufficient to rule out subtle expansion. Even a small outward drift would strengthen the collision hypothesis, while pure rotation would challenge it. Magnetic fields may also hold secrets. In many galaxies, magnetic forces influence how gas collapses into stars, guiding filaments and shaping star-forming regions. If Hoag's object experienced a shockwave, the magnetic field lines may still retain the imprint of that event. Detecting such signatures requires radiopolarization studies challenging at 600 million light-years, but not impossible with future arrays. If unusual magnetic alignments are found, they could point directly to the mechanism that sculpted the ring. Astronomers also examine the environment around Hoag's object for clues. Galaxies rarely evolve in isolation. Interactions leave trails in the surrounding space. If an intruder galaxy once passed through faint tidal debris, should linger beyond the ring stretched into arcs or diffuse clouds. So far, surveys have found no obvious candidates. The silence of the surrounding space is itself puzzling. Did the culprit escape unnoticed, or was the event so ancient that its remains have already dissipated? Even the distribution of globular clusters, ancient compact star swarms, can serve as a record. In many galaxies, their orbits preserve the gravitational memory of past interactions. If Hoag's object hosts an unusual system of globular clusters, offset or misaligned relative to the core, it could be a smoking gun. Detecting them at this distance is difficult, but ongoing deep surveys may yet reveal their presence. Piece by piece, these forensic clues could rewrite the history of Hoag's object. Like detectives sifting through a cold case, astronomers look for anything out of place. A streamer cluster, a polarization signature. Each one is a potential thread that could unravel the mystery. Yet until they are confirmed, the galaxy remains a paradox. A structure that looks impossibly pristine but may secretly carry scars just faint enough to escape our eyes. One proposal that has surfaced in recent years is that Hoag's object may be what astronomers call a fossil galaxy. In this context, the word fossil refers not to bones or shells, but to galactic structures that preserve conditions from an earlier cosmic era. Fossil groups are known in the universe collections of galaxies that merged long ago, leaving behind a dominant elliptical surrounded by a faint halo. Could Hoag's object be a single galaxy version of this phenomenon, a relic that somehow escaped the usual chaos of galactic evolution? Supporters of this idea point to the old metal-rich core. Its stars are ancient, suggesting that it formed very early in cosmic history, perhaps in the first few billion years after the Big Bang. In many galaxies, such cores are later transformed by mergers and accretions, but Hoag's object shows little sign of such disruption. Its spheroid appears intact, undisturbed by the rough encounters that usually shape galaxies over time. To some, this indicates that the central region is a preserved remnant, a galactic fossil in the truest sense. The surrounding ring then would represent a later chapter added onto the ancient fossil core. If fresh gas fell in from the cosmic web or from a faint, long-digested neighbour, it might have settled into an orbiting disk. Instead of forming a full spiral for reasons still unknown, the gas ignited into a sharp-edged ring. The result would be a hybrid, a fossil heart wrapped in a youthful halo. But this scenario is controversial. Fossil systems usually display extended X-ray halos, the glow of hot gas retained for billions of years. Hoag's object does not. Fossil groups also form through violent early mergers, yet the symmetry of Hoag's object suggests anything but violence. Critics argue that calling it a fossil oversimplifies the problem. It replaces one mystery with another. How could a fossil system acquire such a perfectly ordered ring so late in its life without disturbing its ancient core? There is also the issue of timing. The stars in the ring are relatively young, no more than a few 100 million years old. If Hoag's object is a fossil, then this burst of star formation is anomalous, a sudden flare of youth around a system that should be long dead. That kind of rejuvenation is not impossible, but it requires a supply of gas and a trigger, both of which remain unidentified. Without them, the fossil interpretation feels incomplete. Still, the fossil idea continues to attract attention, because it frames Hoag's object as not just an oddity, but a survivor. If true, it would mean we are looking at a preserved galactic core from deep time, encircled by a ring whose origin we do not yet understand. It would make Hoag's object both a relic and an anomaly, a window into the distant past wrapped in a puzzle of the present. For now, evidence is lacking. The fossil hypothesis remains one of several competing explanations, none of which fully resolve the paradox. Like the collision model and the resonance model, it accounts for some aspects while leaving others unexplained. The debate underscores just how unusual Hoag's object is. Even concepts designed to explain rare systems falter in its presence. Spectroscopy has long been the most powerful tool in galactic forensics. By spreading a galaxy's light into its component wavelengths, astronomers can read the chemical composition, age, and motion of its stars as though decoding a cosmic barcode. For Hoag's object, these measurements are especially critical because its appearance alone tells us so little about how it came to be. Only in the spectra do the hidden differences between the core and the ring emerge with sharp relief. One line of investigation focuses on metallicity gradients. In a typical galaxy, metallicity decreases with distance from the centre. The inner regions, where star formation has been intense for billions of years, are rich in heavy elements, while the outskirts contain younger, more metal-poor stars. In Hoag's object, the contrast is not just a gradient but a sharp step. The core is old and metal-rich, resembling an elliptical. The ring is younger and noticeably metal-poor, with abundances closer to pristine cosmic gas. This discontinuity suggests that the ring did not simply evolve from the core's material, but was seeded by an external source. Velocity measurements offer another clue. By examining Doppler shifts across the ring, astronomers can map how stars move relative to the centre. The results show a coherent rotation consistent with a stable disk. But within that stability lie subtle deviations, tiny shifts that could betray expansion or warping. Detecting these requires exquisite precision, often at the limits of current instruments. If expansion is confirmed, it would support the idea of a collision-borne wave. If pure rotation dominates, it implies a more enduring configuration, perhaps shaped by resonance or long-term accretion. Even within the ring, spectroscopy uncovers diversity. Some clusters are slightly older with redder colours, while others shine in the bright blue of massive newborn stars. This hints at sequential star formation rippling outward like concentric waves. Yet the spread in ages is remarkably narrow compared to most galaxies, reinforcing the idea that something unusual synchronized the process. It is as if a single event pressed start across 75,000 light-years. The core's spectrum adds to the puzzle. Its absorption lines are consistent with stars formed early in the universe, enriched rapidly by supernovae and then left to age. But the core shows little sign of ongoing interaction with the ring. There is no strong evidence of gas inflow or outflow between the two regions, no spectral fingerprints of mixing. The isolation is striking. In most galaxies, components blend over time. In Hoag's object, they remain distinct, like two stories told in parallel. Comparisons with other ring galaxies highlight how extreme this separation is. In the cartwheel, for instance, metallicity transitions are gradual and velocity fields show turbulence from the impact. In Hoag's object, the clean division between old and young, metal-rich and metal-poor, settled and active defies those expectations. The galaxy behaves as though two unrelated systems were perfectly aligned, but spectroscopy proves they share the same redshift, the same cosmic distance. They are undeniably one. Astronomers continue to refine these spectral maps, pushing for deeper exposures and higher resolution. Each new dataset sharpens the contrast between core and ring, confirming the discontinuity but leaving its cause unresolved. Until the gradients can be fully mapped from the innermost spheroid to the outermost rim, the story of Hoag's object remains unfinished. If the stars of the ring in Hoag's object are young and metal-poor, then they must have formed from gas that was not heavily processed inside the galaxy's ancient core. That immediately raises a question. Where did the gas come from? Theories of external supply are among the most debated because they propose that the galaxy was not simply shaped internally, but was fed from the outside by sources we can only partially trace. One candidate is accretion from the cosmic web, the vast network of filaments that threads the universe channeling gas into galaxies. In simulations, streams of relatively cool hydrogen can flow directly into galactic halos, bypassing the usual shock heating process that keeps infalling gas hot. Known as cold accretion, this mechanism is thought to have fueled rapid star formation in the early universe. Could Hoag's object represent a rare case where such accretion continued late into cosmic history, depositing fresh gas into a nearly empty orbit around the old core? If so, the ring would be the fossilized imprint of this infall, a visible reminder of how galaxies connect to the cosmic web. Another possibility is that the gas was captured from a vanished companion galaxy. In this scenario, a small neighbour may have been cannibalized by the spheroid at the center, its stars absorbed and its gas expelled into orbit. Over time, that gas would settle into a ring and ignite in a synchronized burst of star formation. The trouble is that we see no obvious remnant of such a companion. No tidal streams, no distorted arcs, no faint stellar debris that usually marks the graveyard of a merger. If a galaxy was consumed, it left behind almost no trace, a vanishing act that challenges expectations. Accretion models also struggle with symmetry. In most galaxies, infalling gas arrives unevenly, creating patchy disks or irregular clumps. Hoag's object, however, is defined by its smoothness. If the ring truly came from an external supply, then that supply must have been distributed with almost mathematical precision, an unlikely coincidence. Unless, of course, dark matter played a guiding role, shepherding the material into a circular orbit where it could ignite. Radio observations of neutral hydrogen provide some support for these ideas. Surveys suggest that Hoag's object contains an extended halo of hydrogen gas beyond what is visible in stars. If this halo is connected to filaments of the intergalactic medium, it could represent the reservoir from which the ring drew its fuel. But confirming such a connection requires mapping gas flows on scales that are difficult at 600 million light-years. Meanwhile, chemical analysis adds to the intrigue. The metallicity of the ring's stars is not just lower than the core's, it is closer to the cosmic baseline, suggesting gas that has not been cycled through many generations of stars. This is precisely the signature expected of material from the cosmic web, or from a gas-rich dwarf galaxy, rather than from the recycled interior of an old spheroid. The chemistry, in other words, points outward. The challenge is proving the case. Without direct evidence of filaments feeding the galaxy or remnants of a donor companion, astronomers are left with circumstantial clues, gas reservoir metallicity contrasts and ring symmetry. Each hints at an external origin, but none yet closes the argument. And so the debate continues: was Hoag's object nourished by the universe itself drawing gas from the web, or by a companion now lost to time? Not all explanations for Hoag's object rely on dramatic external events. Some astronomers argue that its symmetry may have arisen from internal dynamics, subtle resonances that guided gas into a ring without the need for a collision. Resonances are common in galaxies. In barred spirals, for instance, gravity from the central bar can trap gas in orbits, where their periods synchronize, piling material into rings. The Milky Way itself hosts such features. Inner rings near the bar and an outer ring at the Lindblad resonance. Could Hoag's object be an extreme case of this familiar process scaled up to cosmic proportions? The idea is attractive because it explains the absence of tidal debris and the smoothness of the ring. If no collision occurred, there would be no scar tissue, no arc streams or shells. Instead, the ring would be the natural outcome of orbital mechanics, a galaxy sculpted by its own gravity. The golden spheroid at the center could act as the anchor, while a resonance in the surrounding halo corralled gas into a sharply defined orbit, where it collapsed into stars. But problems emerge as soon as the details are considered. Resonance rings in other galaxies are usually embedded in disks shaped by the rotation of a bar. Hoag's object has no such bar and no visible disk either. Its core is round, not elongated, lacking the structures that typically drive resonances. Without a bar, what mechanism could generate the necessary gravitational pattern? Some have proposed that a triaxial dark matter halo one that is not perfectly spherical might create resonant zones herding gas into circular paths. This remains speculative since dark matter cannot be observed directly and the halo shape is uncertain. Even if resonance could explain the existence of a ring, it struggles to account for its size. The outer rim of Hoag's object spans 75,000 light-years, far larger than most resonance rings observed in barred spirals. To produce such a scale, the resonance would need to operate across the entire galaxy, requiring finely tuned conditions that simulations rarely reproduce. The sheer sharpness of the boundary is also unusual. Real resonance rings often blur into their surroundings, whereas Hoag's object is defined with startling clarity. Spectroscopic data add to the tension. If resonance is at work, one might expect gradients in star ages across the ring, reflecting the slow accumulation of gas into resonant orbits. Instead, the stars appear nearly coeval, as though formed in a single burst. This sudden synchrony is more consistent with a shock wave from a collision than with a gradual resonance-driven process. Unless resonance acted in an unusually rapid and efficient way, the data resist the explanation. Still, the resonance model remains on the table because it requires fewer extraordinary assumptions. Unlike collisions, which should leave wreckage, or external accretion, which struggles with symmetry, resonance appeals to a universal mechanism, gravity itself. Perhaps Hoag's object represents an extreme outlier, a galaxy where the right balance of mass rotation and dark matter, halo geometry, aligned to create a once-in-a-billion configuration. But until detailed dynamical modelling can show that such conditions are even possible, resonance remains a hypothesis searching for confirmation. For now, it joins the growing list of partial explanations plausible in some respects, inadequate in others. Hoag's object sits at the intersection of theories, stubbornly refusing to settle into one box. Each new idea illuminates one facet of the puzzle but leaves the whole picture incomplete. Among all the scenarios proposed for Hoag's object, one of the most dramatic is the idea of a perfect bullseye collision. In this picture, a smaller galaxy once plunged directly through the centre of the larger spheroid like an arrow piercing a target. The impact would have sent a powerful shockwave through the gas, of the host compressing it into a rapidly expanding circle. As the wave moved outward, it would have triggered a burst of star formation, leaving behind a blazing ring around a relatively undisturbed core. Computer simulations confirm that such collisions can, under the right circumstances, produce ring galaxies. The appeal of this explanation lies in its ability to account for the synchronized ages of the ring stars. A single event unfolding in a matter of millions of years could ignite tens of thousands of light-years of gas nearly at once. It also explains why the core remains intact. If the intruder was small enough and moving fast enough, it could have passed through without shattering the spheroid. The result would be exactly what we see in Hoag's object, an old central population encircled by a young star-forming ring. But the elegance of the bullseye model is undermined by its improbability. To produce a ring as perfectly round as Hoag's object, the collision must have been almost exactly head-on, with the intruder striking within a fraction of a degree of the galaxy's centre. Even a slight offset would leave the ring lopsided, warped, or torn with tidal debris. Simulations show that such symmetry is exceedingly rare, requiring a cosmic alignment of remarkable precision. The odds that we would happen to catch such an event frozen in time strain credulity. There is also the problem of missing evidence. Where is the intruder galaxy now? In most bullseye systems, the culprit can be found nearby, having passed through and continued on its trajectory. In Hoag's object, no such companion is visible. Either it has vanished into obscurity, perhaps too faint to detect, or it was completely assimilated, leaving no identifiable trace. Yet deep surveys reveal no tidal tails, no faint arcs of stripped stars, no stellar debris that would normally betray the passage of such an encounter. The silence is suspicious. Another inconsistency lies in the dynamics of the ring. In simulated bullseye collisions, the ring expands outward over time, gradually dispersing as its stars drift away from the wavefront. But in Hoag's object, the ring appears not to be expanding significantly. Its stars rotate smoothly around the core, behaving like a settled disk rather than an expanding shot. This suggests that if a collision did occur, the system somehow stabilized far faster than theory predicts. Despite these challenges, the bullseye hypothesis remains popular because it requires no exotic physics. It relies only on gravity gas dynamics and chants the same ingredients that shape other galaxies. The challenge is the precision. Was Hoag's object the beneficiary of a cosmic accident so perfect that it left behind a structure nearly indistinguishable from design? Or are we missing key aspects of the physics that could make such outcomes more common than simulations suggest? For now, the bullseye model stands as both the simplest and the most frustrating explanation. It ties many of the observations together but leaves critical holes unfilled. If Hoag's object is a target struck dead center by a cosmic arrow, then the shooter has vanished without a trace, and the bullseye itself refuses to fade. Whenever astronomers encounter a structure that looks too perfect to be real, one of the first questions they ask is whether it might be an illusion. Hoag's object, with its flawless symmetry, has invited such speculation since the moment it was discovered. Could it be that we are not looking at a single bizarre galaxy at all, but at a trick of perspective or light bending? One early alternative was the chance alignment hypothesis. Perhaps the golden core is a small elliptical galaxy in the foreground, while the blue ring is a separate spiral or irregular system far behind it, aligned just so along our line of sight. At a distance of hundreds of millions of light years, two unrelated galaxies could conceivably appear superimposed, creating the illusion of a single, coherent object. The problem with this idea is that spectroscopy quickly ruled it out. Both the core and the ring show identical redshifts. They are receding from us at the same velocity, which means they exist at the same cosmic distance. This is not two galaxies coincidentally lined up. It is one system. Another proposal was gravitational lensing. In this scenario, the massive core galaxy would act like a lens, bending the light of a background object into a circular arc. We know lensing can create rings, so-called Einstein rings, when the alignment is just right. Could Hoag's object be such a lens with a ring, nothing more than the distorted image of a galaxy far behind it? Again, the evidence speaks against it. Einstein rings produce arcs of light with the same spectrum as the background source. In Hoag's object, the stars in the ring show the same redshift as the core, meaning they belong to the same system. The ring is not lensed light. It is real matter orbiting the galaxy. More exotic ideas have occasionally surfaced. Some have wondered whether Hoag's object could be a kind of hybrid system, two galaxies in the process of merging but not yet overlapping. In this view, the core is the remnant of one galaxy, while the ring is the disk of another captured and wrapped around it. But mergers rarely produce such clean geometry. They leave scars, asymmetries, and streams of stars flung into intergalactic space. Hoag's object shows none of this. If it is a merger, it is one unlike any we have ever seen. These rejected hypotheses are important not because they solved the mystery, but because they narrowed the field. Each test measuring redshift, analysing spectra, modelling lensing effects chips away at the list of possibilities. What remains are the scenarios that fit at least part of the evidence. A bullseye collision, a resonance-driven ring, or accretion from outside. None is fully satisfying, but each has some observational support. The discarded ideas, though less glamorous, help to sharpen the outlines of the puzzle. In the end, Hoag's object defies easy categorization. It is not an illusion, it is not a trick of perspective, it is not a mirage produced by gravity. It is a real galaxy with real stars orbiting in defiance of our models. And that makes it all the more compelling because it forces us to confront the limits of what we know. For most of the 20th century, galaxies were sorted into neat boxes. Spirals, ellipticals, irregulars. This so-called Hubble tuning fork became the standard framework shaping how astronomers thought about galactic evolution. Spirals were gas-rich and star-forming ellipticals were quiescent and ancient, and irregulars filled the margins. But objects like Hoag's object remind us that reality is more complicated than diagrams. The very existence of such a clean ring defies the categories. It is not a spiral, there are no arms, no bar, no obvious disk. It is not an elliptical because it is surrounded by active star formation on a colossal scale. Nor does it resemble an irregular since its geometry is anything but chaotic. In classification terms, Hoag's object zits off the chart in a corner of parameter space that the tuning fork never anticipated. Astronomers have tried to expand the taxonomy to account for such anomalies. Ring galaxies were formally recognized as a rare type with subclasses for collisional rings, resonance rings, and polar rings. Yet Hoag's object stubbornly resists even these expanded definitions. Its symmetry sets it apart from collisional rings. Its lack of a bar excludes resonance rings. Its alignment rules out polar rings. Each box it might fit into comes with caveats, leaving it a category of 1. This matters because classification is not just semantics, it guides theory. If a galaxy cannot be classified, it cannot be easily compared, and its place in the evolutionary story remains unclear. Hoag's object forces researchers to confront whether our models of galactic life cycles are too narrow. If it truly is stable, then our diagrams are incomplete. If it is transient, then we may be missing critical stages in the lives of galaxies. Surveys of deep space have already revealed hints that the universe may harbour more variety than once thought. Faint ring-like structures appear in some datasets, often overlooked or misclassified. New telescopes such as the Vera Rubin Observatory may bring these to light in greater numbers. If more objects like Hoag's appear, they could form a new branch on the evolutionary tree, forcing revisions to the diagrams that have shaped our understanding for a century. In this way, Hoag's object is not just a puzzle in isolation. It is a test of our ability to describe the universe. If even one galaxy lies outside our schemes, then the schemes must adapt. Each attempt to explain Hoag's object is not only about one anomaly, but about the diversity of galactic forms as a whole. And with every data set, the mystery grows sharper. Are we glimpsing a rare exception, or the first signs of a hidden population that challenges the foundations of galactic morphology? Measuring the true scale of any galaxy begins with one of the hardest questions in astronomy. How far away is it? For Hoag's object, the answer matters enormously. Without distance, its apparent size on the sky is meaningless. A dime held at arm's length can look the same as the full moon. Only by pinning down the distance can astronomers say whether the ring spans a few thousand light years, or as it turns out, tens of thousands. Spectroscopy again provided the first clue. By examining the redshift of the galaxy's light, astronomers determined that it is receding from us at a velocity consistent with a distance of roughly 600 million light years. At that range, the ring's angular diameter translates into a physical size of about 75,000 light years, across nearly as large as the Milky Way itself. This immediately elevated Hoag's object from a curiosity to a galactic heavyweight. Not a minor oddity, but a full-scale system. Surface brightness measurements further refine the picture. By comparing the luminosity of the ring's star-forming regions with those of better-studied galaxies, astronomers can cross-check distance estimates and calibrate models of stellar populations. In Hoag's object, the brightness of the blue ring matches expectations for a massive starburst, a few 100 million years old, reinforcing the redshift-derived distance. This consistency strengthens the case that the galaxy is exactly what it appears to be, a giant isolated ring system, rather than a nearby dwarf masquerading as something grander. Hoag's object also serves as a valuable test of the cosmic distance ladder. Each rung of this ladder, from parallax to Cepheids to Type E or supernovae, builds on the others, extending our reach farther into space. Galaxies like Hoag's at intermediate distances of hundreds of millions of light years provide an opportunity to cross-validate methods. Its spectra can be used to estimate distances via the Tully-Fisher relation, comparing rotational velocity to luminosity. Its clusters could in principle host variable stars that act as standard candles. While not as accessible as nearer galaxies, Hoag's object anchors a key segment of the ladder. Even the precision of its geometry aids these efforts. Because the ring is nearly perfect, astronomers can model its light distribution with unusual accuracy. Subtle asymmetries, slight brightening on one side. Gradients in star color become diagnostic tools, offering constraints on how light propagates through the galaxy. These constraints feed back into larger cosmological models, helping refine how we measure and interpret distant systems. In this way, Hoag's object is not only a mystery but also a benchmark. Its clean structure makes it easier to model than most galaxies, while its distance places it in a regime critical for calibrating extragalactic measurements. Each observation contributes not only to the enigma of its origin, but also to the scaffolding by which we measure the universe itself. Hoag's object is not only an isolated enigma, but also a potential probe of cosmology itself. Galaxies are the visible traces of the invisible scaffolding of the universe, the vast cosmic web of dark matter and gas that defines large-scale structure. An object as unusual as Hoag sits at an interesting crossroad. Either it is a rare outlier produced by improbable circumstances, or it reflects conditions in the dark matter environment that we do not yet understand. One way astronomers approach this is by considering the role of dark matter halos. Every galaxy is believed to reside within a massive halo of dark matter that governs its rotation and evolution. In simulations, the shape and density of a halo can strongly influence how gas settles and how stars form. If Hoag's object is truly stable, not the transient scar of a collision, then its halo must be unusually smooth and spherical, capable of guiding gas into a nearly perfect orbit. This raises the possibility that Hoag's object resides in a dark matter environment, unlike the typical triaxial halos predicted by cold dark matter models. Testing this requires comparing its rotation curve and gas distribution to predictions from simulations. Any discrepancy could signal gaps in our cosmological framework. Another cosmological angle is isolation. Hoag's object lies in a relatively sparse region of space, with few nearby galaxies to disturb it. This contrasts with the crowded clusters where most interactions and collisions take place. Its solitude may be part of the reason it survived in such pristine form, but that very isolation makes it a valuable probe of the cosmic web. If cold accretion streams are still feeding it, as some models suggest, then they must do so without the interference of neighbours. Detecting such inflows would provide rare direct evidence of how gas travels along filaments into galaxies, a process central to cosmological simulations but still difficult to observe. The scale of the ring also offers insight into the density of the surrounding environment. In simulations, large coherent rings often disperse unless supported by a smooth potential. If Hoag's object maintains its structure for billions of years, it may imply that the density fluctuations in its local region of the universe are unusually low. That would make it a cosmic laboratory for studying how structure forms not just in galaxies but in the intergalactic medium itself. There is even the question of timing in cosmic history. At 600 million light-years away, we're seeing Hoag's object as it was about 600 million years ago. That is recent by cosmological standards, but still long enough that conditions in the universe were subtly different. Star formation rates were declining, clusters were assembling, and the cosmic web was maturing. If Hoag's object required special conditions to form, such as abundant cold gas or a quiet environment, then its existence tells us those conditions still persisted in its region of the universe relatively late in time. In this sense, the mystery of Hoag's object ripples outward. It is not only about one galaxy, but about the models that describe all galaxies. If our simulations cannot produce objects like it under normal conditions, then perhaps our assumptions about dark matter, halos, accretion flows, or environmental effects need revision. Each failed explanation is not just a local mystery, but a cosmological challenge pointing to where theory must grow. If Hoag's object has resisted explanation for decades, it is partly because our instruments have only been able to scratch the surface of its secrets. But the next generation of observatories promises to push far deeper. Each new telescope carries the potential to reveal another layer of the enigma, from the chemistry of its stars to the flow of its gas and even the shape of its dark matter halo. The James Webb Space Telescope is already revolutionizing the study of distant galaxies with its unprecedented infrared sensitivity. For Hoag's object, Webb can do what Hubble could not: resolve fainter redder stars within both the core and the ring. These stellar populations act as timestamps, allowing astronomers to refine the ages of different regions with much greater accuracy. If the ring stars truly formed in a sudden burst, Webb's data should show a sharp cutoff in their age distribution. If instead star formation was prolonged, it will reveal a spread of ages. Webb's instruments can also detect faint emission lines from ionized gas in the ring, tracing the conditions that ignited the wave of starbirth. The Vera Rubin Observatory, with its wide-field survey power, will take a different approach. Its mission is to repeatedly image the entire visible sky, capturing faint transient and overlooked structures. For Hoag's object, Rubin may detect the faintest possible remnants of past interactions, delicate stellar streams, diffuse arcs, or asymmetries in the halo that earlier surveys missed. If even a whisper of a collision survives, Rubin's deep imaging could expose it. Just as importantly, Rubin may uncover more galaxies like Hoag's, providing the missing context. Is it truly unique or just the most famous example of a hidden population? The answer depends on Rubin's discoveries. The Square Kilometre Array, the world's most ambitious radio telescope, will target Hoag's object in yet another way. Its sensitivity to neutral hydrogen will map the galaxy's gas halo with exquisite detail, revealing whether streams of cold gas are still flowing into the ring. It can measure the velocity of gas clouds as they orbit, tracing the gravitational pull of the dark matter halo. If the halo is unusually smooth, SK will detect the signature in the gas distribution. If inflows from the cosmic web are present, it may capture them directly for the first time. Together, these observatories promise to attack the mystery from every angle. Webb will dissect the stars. Rubin will search the outskirts, and SKA will map the invisible gas. Their combined results may finally allow astronomers to decide between the competing scenarios: collision, resonance, accretion, or something entirely new. And yet there is a lingering sense that Hoag's object may continue to defy us. Every advance in observation brings sharper data, but sometimes sharper data only makes the paradox clearer. Will Webb reveal a perfectly synchronized starburst that theory cannot explain? Will Rubin find node debris where models demand it? Will SK map a halo that contradicts predictions? These are not just possibilities. They are the very outcomes that would cement Hoag's object as a cornerstone of galactic science for decades to come. Every anomaly in astronomy comes with two possible fates. Either it is eventually explained within the framework of existing theories, or it forces a revision of those theories themselves. Hoag's object has lingered on the edge of these paths for more than 70 years, resisting neat classification and tidy models. With new observatories on the horizon, the stakes are higher than ever. If Webb Rubin and the Square Kilometre Array cannot close the case, then Hoag's object will pass into a different category altogether. Not just an oddity, but a Rosetta Stone for galactic science. The comparison is deliberate. Just as the Rosetta Stone allowed linguists to decode Egyptian hieroglyphs by providing a new framework of translation, Hoag's object could provide the key to unlocking hidden rules of galactic formation. If its ring truly formed without a collision, then we must expand our understanding of how gravity and dark matter halos can orchestrate large-scale structures. If the ring came from an invisible inflow of gas, then our models of cosmic accretion must be updated to account for phenomena we thought had ended billions of years ago. And if it was born of a collision, yet one that left no debris, then our simulations of galactic encounters are missing essential physics. In all scenarios, the object serves as a stress test. Our theories are only as strong as their ability to explain the outliers. When galaxies like Hoag's appear, either the theories bend to fit them or they break and demand repair. This is why anomalies matter so deeply to scientists. They are nature's way of telling us where we are wrong. Already, Hoag's object has forced cosmologists to rethink the neat Hubble tuning fork of galaxy classification. It has forced simulators to push their models to extremes, searching for rare conditions that might reproduce its geometry. It has forced observers to refine their methods, developing deeper imaging techniques and higher resolution spectroscopy. Even without definitive answer, it has advanced the field by sheer defiance. But the true leap will come if the mystery endures even under the glare of 21st century instruments. In that case, Hoag's object will not simply be a curiosity, but a guidepost, a galaxy, pointing the way toward missing pieces in our cosmological story. It may compel us to consider new interactions between dark matter and baryons, new modes of gas accretion, or new pathways of galactic stabilization. It may even hint that our current picture of galaxy evolution is incomplete in ways we cannot yet imagine. And perhaps that is the ultimate role of such anomalies. Not to be explained away, but to force us to grow. If Hoag's object survives every test still standing as a structure without precedent, then it will earn its place alongside the great scientific enigmas, not as a solved puzzle, but as the key to unlocking puzzles yet to come. Hoag's object may be the poster child of cosmic anomalies, but it is not the only galaxy that challenges our expectations. To understand its place in the broader landscape, astronomers often compare it to other peculiar systems, galaxies, that also defy the neat categories of spirals, ellipticals, and irregulars. Among them, the Cartwheel Galaxy looms large. The Cartwheel is perhaps the most famous collisional ring galaxy, located about 500 million light-years away in the constellation Sculptor. Unlike Hoag's object, the Cartwheel's violent past is obvious. Its bright blue ring is ragged, studded with clumps of star formation, and riddled with asymmetries. Streams of stars arc outward like spokes, betraying the turbulence of a smaller galaxy that punched through its centre. Where Hoag's object is smooth and symmetrical, the cartwheel is chaotic and scarred. The comparison highlights just how strange Hoag's perfection is. Most rings wear the marks of their birth, but Hoag's appears almost untouched. Other ring galaxies add to the spectrum. Some show double rings, nested structures where waves of star formation ripple outward. Others are off-centre, their rings elliptical rather than circular, the result of impacts that missed the mark. These systems demonstrate the range of outcomes when galaxies collide. Yet none approach the clean geometry of Hoag's object, which looks less like a wound and more like a design. Polar ring galaxies represent another class of oddity. In these, a spheroidal galaxy hosts a ring of gas and stars orbiting nearly perpendicular to its main body. Such configurations are rare, but they do exist often, formed by accreting material from a companion. Polar rings can appear striking, with luminous bands slicing across their hosts. At first glance, Hoag's object seems similar, an isolated core wrapped by a ring. But the difference is crucial. In polar systems, the ring is tilted, misaligned, and usually irregular. Hoag's ring lies in the same plane as its core, aligned with mathematical precision. Even more exotic are galaxies with detached shells, arcs or ripples in their outskirts, the signatures of past mergers. These features hint at hidden histories, evidence of cannibalism etched into the halo. But again, Hoag's object does not share this messiness. Its halo, as far as we can see, is silent. By setting Hoag's object against these other peculiarities, its uniqueness becomes sharper. The universe produces many ways to bend and twist galaxies, from collisions to accretion to resonance. Each leaves behind scars, asymmetries, or irregularities. Hoag's object alone presents itself as flawless, as though sculpted deliberately. That is why it commands so much attention, not because ring galaxies are unheard of, but because none match its eerie perfection. In this way, Hoag's object is not only a mystery, but also a measuring stick. By contrasting it with galaxies like the cartwheel, astronomers can refine what truly counts as unusual. The comparison makes one truth inescapable. Even in a universe of billions of galaxies, Hoag's object remains a category of one. Astronomy thrives on patterns, but those patterns are rarely perfect. Spiral galaxies, while graceful show arms that twist irregularly with clumps, gaps, and distortions. Ellipticals are smooth only at a distance. Up close, their stars reveal subtle asymmetries and histories of cannibalism. Even ring galaxies, as dramatic as they look, almost always display lopsided edges, patchy starbursts, or tidal debris. That is why Hoag's object is so unsettling. Its geometry is not just unusual, it is uncannily precise. The ring forms a near-perfect circle, 75,000 light-years across, wrapped evenly around a golden spheroid. The gulf between them is almost empty, a dark moat where few stars intrude. No arcs or spokes break the symmetry. No tidal streams arc outward. For a structure created by chaotic forces, gravity collisions, and turbulence, it looks alarmingly like an idealized diagram. Nature rarely sketches with a compass, yet here the lines are almost mathematical. This perfection makes some astronomers uncomfortable because it clashes with expectations. The universe is messy. Galaxy formation is a story of violence. Mergers, accretion, starbursts, and collapse. Out of that chaos emerge beautiful structures, but always tinged with scars. Hoag's object seems to lack those scars. If it is the product of a collision, where is the wreckage? If it grew from resonance, why is the ring so smooth? If it was fed by accretion, why is the distribution so even? Each hypothesis runs into the same wall. The geometry is too clean. Symmetry is not impossible in nature, but it is fragile. Small perturbations tend to grow over time, warping circles into ellipses, distorting disks into spirals. That Hoag's object has preserved its shape suggests either that it is very young, caught in a fleeting stage, or that it is stabilized by mechanisms we do not yet grasp. Both options are problematic. If it is young, the odds of observing it at just the right moment are slim. If it is stable, then our models of galactic dynamics are missing something fundamental. This is why Hoag's object sparks so much debate. It is not simply beautiful, it is suspiciously beautiful. In a universe where chaos rules, symmetry demands explanation. Astronomers are trained to distrust perfection because it usually means that some hidden factor is at work. Just as a perfectly round pebble on a beach hints at long processes of erosion, a perfectly round galaxy hints at forces we do not yet understand. The irony is that this same perfection makes Hoag's object one of the most visually striking galaxies known. Its elegance draws the public eye, inspiring fascination and wonder. But for scientists, that same elegance is an irritant, a reminder that the universe is still capable of producing things that mock our categories and elude our equations. In modern astronomy, simulations are as vital as telescopes. By encoding the laws of physics into algorithms and unleashing them on supercomputers, astronomers can watch virtual galaxies collide, merge and evolve across billions of years. These digital universes have reproduced spirals, ellipticals, bars, and even chaotic mergers with astonishing fidelity. But when researchers attempt to recreate Hoag's object, the results have been far less convincing. The simplest approach is to model a head-on collision, the classic bullseye impact. In these simulations, a small companion plunges through the center of a larger galaxy, generating an expanding shockwave that sweeps gas into a ring. The models do produce rings, sometimes spectacular ones, but they are rarely so perfectly circular. More often, the results resemble the cartwheel galaxy, lopsided with spokes and arcs of debris. Hoag's symmetry remains elusive. The simulations also predict that the ring should expand outward over time, leaving gradients in star ages. Yet in Hoag's object, the stars appear nearly coval, as if the burst was frozen in time. Other teams have tried resonance-driven models setting up galaxies with triaxial dark matter halos or weak bars. These can generate rings under certain conditions, but the rings are typically smaller, fuzzier, and embedded in disks. None produce the clean separation of a luminous ring around a nearly empty void. Worse resonance rings tend to persist only if gas continues to flow inward and outward, creating signs of mixing. In Hoag's object, the isolation between core and ring is stark, as though the two have been quarantined from each other. Cold accretion models offer another avenue. By feeding gas into a spheroid from carefully tuned filaments, simulations can create extended disks or partial rings. But the inflows are turbulent, producing patchy structures rather than a flawless circle. Symmetry does not emerge naturally. It must be forced by fine adjustments to initial conditions. Astronomers call this fine-tuning, and it is generally seen as a weakness in a theory. Nature tends not to arrange such precision unless a hidden mechanism enforces it. Even hybrid models have fallen short. Attempts to combine a collision with resonance effects or accretion with halo shaping can generate rings closer to Hoag's, but only fleetingly. The structures collapse within a few 100 million years, dispersing or deforming. To match Hoag's object, the galaxy would need to be observed in a very narrow window of time, again raising the problem of coincidence. The failures of these simulations are as instructive as they are frustrating. They highlight the gap between what we expect from the physics of gas stars and dark matter, and what we actually see in the sky. In some sense, Hoag's object is less a galaxy than a stress test for our models. If our digital universes cannot produce it, then our digital universes are incomplete. Astronomers are not giving up. With ever more powerful computing resources, new generations of simulations are being designed with higher resolution and more complex physics, including magnetic fields, feedback from supernovae, and the influence of cosmic environments. Whether these refinements will finally conjure a galaxy as eerily perfect as Hoag's remains to be seen. For now, the gap between observation and simulation is wide, and Hoag's object sits firmly on the side of the unexplained. Galaxies are bound by the laws of physics as we know them: gravity, angular momentum, hydrodynamics, and the invisible scaffolding of dark matter. These rules have been tested across countless systems, from dwarfs to giants, and have proven remarkably successful in explaining why most galaxies look the way they do. But Hoag's object seems to lean against the edges of those rules, pressing on weak spots that few others expose. The first challenge is stability. A ring 75,000 light-years wide should be fragile. Small asymmetries in gravity, turbulence in gas, or interactions with nearby galaxies should twist it, warp it, or tear it apart. And yet Hoag's object maintains an almost geometric perfection. This hints at an underlying stabilizing mechanism, either an unusually smooth dark matter halo or a dynamical resonance we have not fully described. In either case, our assumptions about how galaxies settle into equilibrium may be incomplete. The second challenge is isolation. In most galaxies, components exchange material. Gas flows inward, stars migrate, and clusters scatter. Over billions of years, these processes blur distinctions, erasing the clean lines between core and outskirts. Hoag's object defies this. The gulf between its golden spheroid and its blue ring remains stark with little evidence of mixing. This raises the question, are our models underestimating the degree to which gravitational systems can compartmentalize preserving boundaries longer than expected, or is there an unknown factor enforcing the separation? Dark matter plays a central role in both puzzles. Simulations predict that halos are triaxial, stretched and lumpy, not perfectly round. Yet Hoag's object seems to require a halo of exceptional smoothness, capable of sustaining a perfectly circular orbit for billions of stars. If such halos exist, they are rare, and their rarity has implications for cosmology itself. Alternatively, if halos are generally smoother than we think, then much of our picture of large-scale structure may need revision. There is even a more radical possibility. Some researchers have speculated that objects like Hoag's could test modifications to gravity itself. Alternatives to dark matter, such as Mund-modified Newtonian dynamics, predict different outcomes for the rotation of galaxies and the stability of rings. While Hoag's object alone cannot decide between competing theories, its unusual dynamics make it an intriguing laboratory. If its stars orbit in ways inconsistent with either cold dark matter or Mund, then something deeper may be at play. At its heart, Hoag's object is not just a curiosity but a stress test for the foundations of galactic dynamics. It pushes at assumptions that usually go unquestioned, that halos are lumpy, that mixing is inevitable, that collisions leave scars. Each clean circle of its ring, each untouched gap in its core is a quiet challenge to our equations, and that challenge echoes beyond one galaxy. Because if our models cannot explain Hoag's object, then they may be missing truths about the universe itself. When most people first see Hoag's object, their eyes are drawn to the luminous ring, the flawless circle of blue stars glowing like a cosmic halo. But for astronomers, the dark gulf that separates the ring from the core is just as fascinating, perhaps even more so. This empty zone, tens of thousands of light-years wide, holds critical clues to the galaxy's history. It is not only what we see in Hoag's object that matters, but what we do not. In spiral galaxies, regions between the core and arms are filled with gas dust and intermediate populations of stars. Even collisional ring galaxies like the Cartwheel often show debris streams and patchy light inside their rings. Hoag's object defies this expectation. The space between its golden spheroid and blue ring is strikingly clean, devoid of significant star formation or lingering gas clouds. The emptiness is so complete that it looks artificial, as though someone carved a moat around the core. This absence presents two puzzles. First, if the ring formed from an outward moving shockwave, as in the bullseye collision model, why has no residual star formation been triggered in the wake of the wave? In simulations, material left behind typically ignites smaller bursts as it collapses under gravity. Yet Hoag's object's interior remains quiescent, a silent void, where no such secondary activity occurs. Second, if the galaxy is sustained by cold accretion from the cosmic web, why has none of the gas fallen inward to populate the intermediate region? Instead, the inflows appear to have skipped the inner zones, entirely depositing material directly into the outer orbit. Spectroscopic surveys confirm that the gulf is not simply dark because it is faint. The lack of emission lines means there is little ionized gas, and the absorption features show few intermediate-age stars. It is by galactic standards truly empty. This sharp division reinforces the idea that Hoag's object is compartmentalized. An ancient core, a pristine ring, and little in between. The void may also act as a stabilizer. With no competing gravitational masses inside the ring, the orbits of its stars can remain remarkably clean, free of disturbances that would otherwise warp the structure. In this sense, the absence of matter is not just a curiosity, but a feature part of what allows the ring's symmetry to endure. Yet this only raises the deeper question. How did such a void form in the first place, and how has it been maintained for hundreds of millions of years? Some astronomers speculate that dark matter plays a role here too. If the central spheroid sits within a dense, smooth halo, the gravitational potential could naturally suppress the accumulation of material in the inner regions. Gas drawn in might bypass the interior and settle farther out, creating the ring. But if so, Hoag's object is one of the clearest demonstrations of dark matter, shaping not just the rotation of galaxies, but their very architecture. In the end, the emptiness between the core and the ring is not a blank space, but a message. It tells us that something has prevented the normal processes of mixing, collapse, and star formation that fill most galaxies. Whether it is the aftermath of a collision, The imprint of a resonance or the sculpting hand of dark matter, the void is part of the riddle. Without it, Hoag's object would be strange. With it, the galaxy becomes nearly incomprehensible. When optical images show emptiness, astronomers turn to other wavelengths to test whether the void is truly barren. Light we see with our eyes is only a fraction of the electromagnetic spectrum, and galaxies often reveal different personalities when viewed in infrared, ultraviolet, or radio. Hoag's object has therefore been subjected to a multi-wavelength investigation with the goal of uncovering whether its dark gulf conceals faint traces of gas dust or hidden stars. Infrared observations were the first to probe the gap. Instruments sensitive to thermal emission can detect cooler stars, long-lived red giants, and dust grains heated by starlight. In spiral galaxies, these features often fill the spaces between arms. In Hoag's object, however, infrared maps confirmed what optical images suggested. The void is remarkably clean. Only the faintest diffuse emission is present, far below what would be expected if a significant population of older stars or warm dust lingered there. This rules out the possibility that the gulf is merely an illusion created by dust obscuration. Ultraviolet surveys provide a complementary test. Young, massive stars emit strongly in ultraviolet wavelengths, making this part of the spectrum a sensitive tracer of recent star formation. If the shock wave that produced the ring had left residual activity in the interior, ultraviolet light would betray it. Yet deep UV imaging shows no significant glow from the gulf. The starburst was confined almost entirely to the outer ring, leaving the interior in silence. The message is consistent. Whatever event shaped Hoag's object, it avoided the middle ground. Radio telescopes extend the search to neutral hydrogen gas, the raw fuel for future stars. Many galaxies that appear quiescent in visible light are revealed to contain vast stores of hydrogen at radio frequencies. In Hoag's object, radio mapping has detected a halo of hydrogen extending beyond the ring, but little concentrated material inside the gap. The gas reservoir seems to have skipped the void, settling into orbits that coincide with the star-forming ring. This reinforces the picture of a system sharply divided into zones. A gas-poor core, an empty gulf, and a gas-rich ring. Even X-ray observations have been considered. Hot gas trapped in halos or stirred by past collisions often shines in X-rays, filling the regions around galaxies. Hoag's object, however, is faint in this regime. No bright X-ray halo envelops the void, suggesting that it is not filled with hot plasma either. If the galaxy once experienced a violent event, its gaseous aftermath has long since dispersed, leaving behind little trace in the interzone. Across the spectrum, the story repeats. Optical, infrared, ultraviolet radio, and X-ray data converge on the same conclusion. The gulf is genuinely empty, at least to the limits of our detection. For scientists, this is both satisfying and maddening. It rules out certain explanations: no hidden dust lanes, no buried star clusters, no invisible gas clouds waiting to collapse. But it also deepens the mystery. If nothing occupies the void, why does the ring exist where it does? Why should star formation switch on precisely at 75,000 light-years and nowhere inside? The absence of hidden matter makes Hoag's object even harder to explain. The void is not a veil, it is real. And in astronomy, sometimes emptiness is the most profound signal of all. One of the strangest features of Hoag's object is not simply that it has a ring, but that the ring sits at a very precise distance from the core, 75,000 light-years. Not closer, not farther, but locked into a radius that has persisted for hundreds of millions of years. The sharpness of this boundary demands explanation. Why does star formation turn on at that point, and why is everything inside so barren? The first idea is gravitational resonance. In many galaxies, orbital resonances act like invisible traffic controllers, piling material into specific zones. Stars and gas clouds moving through a galaxy may find themselves repeatedly tugged by the same gravitational rhythm, much like a child on a swing pushed at just the right moment. Over time, these nudges corral matter into rings. Perhaps Hoag's object represents an extreme case with its dark matter halo tuned in such a way that gas could only settle at the 75,000 light-year mark. The symmetry of the result would then reflect the underlying symmetry of the halo itself. Another explanation invokes the concept of stability boundaries. In rotating systems, not all orbits are equally stable. Some radii allow stars and gas to move smoothly for billions of years, while others are chaotic, prone to collapse or dispersal. If Hoag's object's halo supports one particularly stable orbit at this radius, then gas falling inward might naturally pile up there like debris trapped at the edge of a whirlpool. The sharpness of the ring would then be a reflection of physics, not chance. A third possibility is that the position of the ring marks the relic of an ancient event, the shock front from a collision or accretion that deposited material exactly at that orbit. If so, the distance tells us something about the energy of the event and the structure of the core it passed through. Like ripples on a pond, the wave would have expanded until it reached equilibrium at 75,000 light-years, freezing into the glowing band we see today. Spectroscopic studies offer tentative support for the idea of a privileged radius. The stars within the ring rotate with surprising smoothness, showing little of the scatter that plagues orbits elsewhere. This suggests that the location is dynamically favoured a natural basin of stability. Yet whether that basin is carved by resonance, by dark matter, or by the memory of a collision remains uncertain. What makes the puzzle sharper is the precision of the cutoff. Star formation does not fade gradually inside the ring. It stops. The void is almost total, as if some unseen barrier prevents gas from crossing into the inner regions. No known law of galactic dynamics predicts such a clean divide. It is as though nature drew a line invisible but absolute and declared, "Here the stars may shine, but no farther in." For astronomers, this specificity is maddening. Random chance could produce a ring, but why here, why now, and why so perfect? Unless an unknown mechanism is at work, the location of Hoag's ring remains one of its most tantalizing mysteries. The mystery of why Hoag's object's ring sits exactly where it does inevitably leads astronomers to one invisible player: dark matter. Though unseen dark matter is believed to make up most of the galaxy's mass enveloping the luminous core and ring, in a vast halo that dictates how stars and gas move. If the ring occupies such a specific radius, then it may be telling us something about the shape and density profile of that halo. In standard models, dark matter halos are not perfectly round. Simulations suggest they are triaxial, stretched lumpy and irregular. Yet Hoag's object looks as if it is embedded in a halo of remarkable smoothness. Its ring is almost perfectly circular with a little sign of warping or distortion. This symmetry hints that the underlying gravitational potential may itself be unusually spherical. If true, Hoag's object could represent one of the cleanest natural laboratories for testing halo geometry. Rotation curves offer the first evidence. By measuring the velocities of stars and gas in the ring, astronomers can map how gravity changes with distance from the core. Early results show that the velocities are consistent with a massive halo extending well beyond the visible ring. But the smoothness of the rotation with little scatter or asymmetry suggests that the halo is more isotropic than most simulations predict. If confirmed, this could challenge the standard picture of cold dark matter, which generally produces clumpier structures. The position of the ring may also correspond to a natural minimum in the gravitational potential, a radius where orbits are especially stable. If dark matter halos have such features, they could act as traps, guiding in falling gas into narrow bands where it accumulates and forms stars. In most galaxies, turbulence and mixing erase these patterns, but in Hoag's object, isolation and symmetry may have preserved them. The ring then would be a visible imprint of the invisible halo, a glowing outline drawn on the sky by dark matter itself. Some researchers have proposed that studying Hoag's object in detail could test whether dark matter behaves exactly as expected. If the halo truly is smoother than predicted, it might indicate new physics. Self-interacting dark matter that redistributes itself into more isotropic shapes or exotic particles that alter halo structure. Such possibilities extend the significance of Hoag's object beyond galactic dynamics, touching on the very nature of matter in the universe. Future observations will be critical here. The square-kilometre array's maps of neutral hydrogen could trace the halo's gravitational influence far beyond the ring, while precise measurements of stellar velocities with next-generation instruments could refine the rotation curve. If these data reveal deviations from the cold dark matter model, Hoag's object will have forced a profound rethinking of cosmic structure. For now, the galaxy remains a tantalizing clue. Its flawless ring is not only beautiful but diagnostic, a marker that points straight at the hidden hand shaping the cosmos. If we can decode what that marker means, Hoag's object may become one of the most important galaxies in the search for the true nature of dark matter. Dark matter remains one of the deepest mysteries in modern science. We infer its presence from gravitational effects, but its nature is unknown. Is it composed of heavy, slow-moving particles, the classic cold dark matter? Is it made of lighter, faster particles, the so-called warm dark matter? Or does it even interact with itself, redistributing its density in ways our models have yet to capture? Hoag's object, with its improbable geometry, may provide a rare natural stage on which to test these competing ideas. In the cold dark matter framework, halos are expected to be clumpy with substructures orbiting within them. These subhalos often stir up gas, creating asymmetries in galaxies. If Hoag's object resides in such a halo, the ring should display irregularities, subtle warps, or density enhancements where the subhalos tug. Yet the ring is astonishingly smooth. Its near-perfect circle suggests either that it lives in a halo stripped of substructure, or that dark matter is behaving differently here than standard cold models predict. This discrepancy makes Hoag's object a potential stress test for the cold dark matter paradigm. Warm dark matter offers another angle. Because the particles move faster, they erase small-scale clumps in halos, producing smoother distributions. A warm dark matter halo could in principle explain the symmetry of Hoag's object, as it would lack the lumpy substructure that cold dark matter predicts. If future measurements of its rotation curve and gas dynamics show an unusually smooth gravitational field, astronomers may find themselves compelled to consider warm dark matter as a more plausible explanation. Then there is the self-interacting dark matter hypothesis. In this model, dark matter particles can collide and scatter with one another, redistributing energy and producing halos that are rounder and more isotropic. Such a halo would naturally lend itself to a structure like Hoag's object, where gas is shepherded into a uniform orbit. If confirmed, this would represent one of the strongest indirect arguments for self-interacting dark matter, a model that has long intrigued cosmologists but has been difficult to test. Each of these scenarios makes distinct predictions. Cold dark matter expects substructure that should subtly distort the ring. Warm dark matter expects smoother halos but predicts certain limits on galaxy formation that may or may not fit Hoag's object. Self-interacting dark matter expects spherical halos that could align neatly with what we see, but only if the interaction cross-section is tuned just right. By studying this galaxy in detail, astronomers could constrain which of these models is most compatible with reality. This is what makes Hoag's object so powerful as a laboratory. Its simplicity, an old core, a clean void, a perfect ring strips away the complications that make most galaxies hard to model. Instead, it presents a clean experiment set by nature, isolating the gravitational fingerprint of dark matter. If the data cannot be reconciled with cold dark matter, it would be a profound clue. If warm or self-interacting models provide a better match, then Hoag's object may become a cornerstone of the next generation of cosmological theory. In the end, the strange beauty of this galaxy may be more than aesthetic. It may be the signpost pointing us toward the true identity of the invisible matter that binds the cosmos together. To probe the unseen, astronomers follow motion. Stars and gas are test particles in a cosmic experiment tracing out the shape of the gravitational potential that binds them. In Hoag's object, the perfect ring is more than a visual oddity. It is also a laboratory of orbital mechanics where every star and gas cloud encodes information about the invisible halo. Measuring their velocities with precision may hold the key to deciding which model of dark matter, if any, best describes reality. In the cold dark matter framework, the ring should not remain perfectly uniform. Subhalos of dark matter orbiting within the main halo would subtly disturb the motion of stars. Over time, such disturbances would produce clumps or asymmetries in the velocity field, patches where stars rotate faster regions where gas flows are offset. If astronomers map the ring in high detail and find no such irregularities, it would cast doubt on the standard cold dark matter scenario, at least for this galaxy. Warm dark matter predicts a smoother potential. Without small clumps, the velocity field should look far more regular with rotation curves that are stable and symmetric across the ring. If Hoag's object exhibits exactly this pattern, a velocity field smooth to within a few kilometers per second across 75,000 light-years, it would lend support to the idea that warm dark matter particles are erasing the substructure predicted by cold dark matter models. Self-interacting dark matter offers a different prediction. In this model, collisions between dark matter particles isotropize the halo, redistributing density and producing a more spherical gravitational field. The effect would be subtle but detectable. The velocity dispersion of stars would be lower with fewer random motions superimposed on their rotation. Gas clouds would also settle into more stable orbits, producing an even sharper ring edge. If future instruments detect unusually low velocity scatter in Hoag's object, it could serve as indirect evidence for self-interactions. Spectroscopic surveys are the tool of choice here. By measuring Doppler shifts in the light from individual star clusters or gas knots within the ring, astronomers can build a velocity map across the entire structure. Already preliminary data suggest rotation is smooth, but the resolution is limited. The next generation of observatories, from 30-meter class telescopes on Earth to the James Webb Space Telescope's infrared spectrographs, could achieve the precision needed to discriminate between models. Radio observations of neutral hydrogen will add another dimension. Gas clouds are easier to track than stars as they emit strong narrow spectral lines. Mapping the motion of hydrogen in Hoag's object could provide a rotation curve extending well beyond the visible ring, revealing whether the halo is clumpy, smooth, or spherical. Each outcome ties directly to a different dark matter hypothesis. Ultimately, Hoag's object offers something rare, a clean geometric structure where gravitational effects can be isolated and tested with minimal confusion. Unlike messy spirals or irregular mergers, the ring is simple enough to model yet large enough to feel the full influence of the halo. Every kilometre per second of stellar motion is a clue, every line in a spectrum a window into the unseen. If dark matter leaves its fingerprint anywhere, it will leave it here. In astronomy, the term standard candle usually refers to objects of known luminosity such as Cepheid variables or TPEA supernovae, which allow us to measure distances across the cosmos. But Hoag's object suggests another more metaphorical use of the phrase. With its uncanny geometry and improbable stability, it may serve as a galactic standard candle of a different sort, a reference point for testing how stable complex structures can be, and how well our theories of dark matter and gravity can account for them. The idea begins with the ring itself. Most ring galaxies are transient, expanding shockwaves that blur and dissolve over time. Hoag's object does not look transient. Its stars orbit with the smoothness of a settled disk, and its edges remain sharp after hundreds of millions of years. If it is still coherent long after its supposed birth event, then its endurance becomes a measure of stability. By modelling how long such a ring could survive under different conditions, astronomers can use Hoag's object as a benchmark. If simulations predict that no ring should last this long, but Hoag as clearly has, then our understanding of galactic dynamics is incomplete. The galaxy may also serve as a test for how dark matter distributes itself. If a spherical isotropic halo is required to preserve the ring's symmetry, then Hoag's object becomes the exemplar case. Its structure would act as a litmus test. If a given model of dark matter cannot produce a stable circular ring like this, then the model fails. In this sense, the galaxy is a standard against which theories are measured even if it is unique in the sky. Astronomers could also track whether the ring evolves over time. If the stars are dispersing outward, or if new clumps of star formation appear, the changes would provide a timeline of stability. By monitoring Hoag's object across decades with successive generations of telescopes, we can turn it into a living experiment. Does it remain frozen, or does it slowly shift? Either outcome is valuable. If it changes, we learn about the transient lives of ring galaxies. If it does not, we learn about the deeper physics that locks it into place. There is even the possibility of using Hoag's object as a calibration tool for simulations. In the same way, astronomers check models of supernova explosions against observed light curves. They could check galaxy formation models against Hoag's symmetry. If the ring's persistence, geometry, and dynamics cannot be matched, then the simulation has failed an essential test. The object thus becomes not only a mystery but a standard candle in the metaphorical sense, a reference of what is possible in the universe and a challenge to replicate it. In this way, Hoag's object transcends its role as a single anomaly. It becomes a tool, a cosmic ruler against which we can measure the accuracy of our theories, the power of our simulations, and the truth of our assumptions. It is rare for one galaxy to take on such significance, but Hoag's object may well be one of those rare benchmarks shining not just as a curiosity, but as a galactic standard candle for the physics of structure itself. Galaxies evolve over billions of years, their shapes shifting slowly as stars are born, live and die. In this grand timescale, most of what we observe are long-lived states, spirals that can persist for billions of years, ellipticals that drift quietly across cosmic epochs. But what if Hoag's object is not a stable anomaly, but a fleeting moment in galactic transformation, a snapshot of something rare caught by chance? One possibility is that Hoag's object is a transition between two more familiar states. Perhaps it began life as a spiral galaxy, its arms eventually stripped away by a subtle encounter or gravitational tides. The stars of those arms might have migrated outward, forming the ring, while the core condensed into its spheroid. If so, the Hoag's object we see today is not permanent but a stage on the way to becoming a more conventional elliptical. If this is true, then the flawless ring is only a temporary arrangement destined to dissolve in another few 100 million years. Another scenario is that Hoag's object was created by an unusual type of collision. In many ring galaxies, the circular structure expands and dissipates as the shockwave loses energy. What makes Hoag's object different could be timing. We might be observing it in a narrow window where the ring has expanded to its current size, but before it begins to break apart. The fact that we see it now in this pristine state may be nothing more than cosmic luck, a reminder that astronomy often depends on catching the universe in the right moment. If Hoag's object truly represents a transitional phase, its rarity makes sense. Billions of galaxies exist, but only a handful resemble Hoag's. The odds of seeing one in this exact stage are low, which explains why we struggle to find close analogues. Its existence, then, is a statistical outlier, improbable but not impossible in the vast sample size of the universe. Yet the longer we study it, the more stable it appears. The ring shows little sign of dispersing, the void remains sharp and the core is undisturbed. If this is a transition, it is a remarkably slow one. It may be that we are witnessing a galactic metamorphosis stretched across hundreds of millions of years, so gradual that it masquerades as permanence. For humans bound to short lifespans, such timescales blur the line between transient and eternal. Astronomers continue to wrestle with the question: is Hoag's object an equilibrium state sustained by dark matter or a fleeting accident soon to fade? Either answer is profound. If it is stable, then our models of galactic dynamics must change to explain it. If it is transient, then we must accept the incredible luck of seeing it now at just the right stage, a cosmic butterfly caught mid-emergence. In astronomy, one way to understand a mystery is to look for comparisons. A single object can always be dismissed as an outlier, but a population hints at a pattern. For decades, astronomers have scoured the sky for galaxies that resemble Hoag's object, a central spheroid surrounded by a clean detached ring. The results have been sparse, almost discouraging. Hoag's object seems to stand nearly alone. There are other ring galaxies, to be sure. The Cartwheel Galaxy is the most famous, its bright ring formed by a violent collision. Smaller ringed systems pepper the catalogues, many showing irregular arcs or warped structures, but none share Hoag's perfect symmetry. In every case, either the core is distorted, the ring is uneven, or the void is not as sharp. Hoag's object is not just rare, it may be unique. Catalogues from surveys such as the Sloan Digital Sky Survey and the Hubble Space Telescope have turned up a few candidates objects with detached rings and spherical cores. Astronomers call them Hoag-type galaxies, yet each time closer inspection reveals differences. The rings are elliptical, not circular. The cores show signs of bars or disks. The gaps are not as clean. These lookalikes never quite match the original. Hoag's object remains the benchmark against which all others fall short. Why is this? One answer is that the conditions required to produce such a structure are extraordinarily specific. If it is a collision, the impact must be perfectly centered and balanced. If it is resonance, the halo must be unusually smooth. If it is accretion, the flow of gas must be finely tuned. Any deviation results in a symmetry warping or collapse. In other words, the universe does not forbid galaxies like Hoag's object. It just makes them vanishingly difficult to form. Another explanation is observational. Even if Hoag-type galaxies exist, they may be rare and distant, hidden among billions of other systems. Their rings could be faint, requiring deep imaging to detect. Future surveys, such as those from the VRC, Rubin Observatory may uncover more examples simply by scanning wider and deeper. If more are found, we may begin to classify Hoag's object not as a unique oddity, but as the best-known member of a very rare class. For now, though, it remains a solitary specimen. Its scarcity intensifies its mystery. If it were common, we could build statistical models, chart variations, and compare lifetimes. But with one clear example, every theory balances on a knife's edge. Was Hoag's object formed by chance a cosmic accident never to be repeated? Or is it the visible tip of a hidden population waiting for our telescopes to grow powerful enough to reveal them? The search continues, driven by the hope that somewhere in the depths of sky surveys or the archives of future missions, another perfect ring lies waiting. Until then, Hoag's object keeps its crown, a galaxy without peers, an almost impossible geometry that defies duplication. The quest to uncover whether Hoag's object is unique or part of a hidden family now rests in the hands of the next generation of sky surveys. For the first time, humanity is building instruments capable of scanning vast regions of the cosmos, with both depth and detail revealing faint structures that were once invisible. Among these, the Vera C, Rubin Observatory and the European Space Agency's Euclid mission stand out as game changers. The Vera C, Rubin Observatory perched on a mountaintop in Chile, will soon begin its legacy survey of space and time. Over a 10-year mission, it will capture the entire southern sky every few nights, building a dynamic, multicolour map of billions of galaxies. Its wide field and sensitivity mean that faint rings, detached arcs or subtle structures will no longer go unnoticed. For galaxies like Hoag's object, with tenuous rings that might fade into the background in smaller surveys, Rubin's images could provide the first statistical census. Even if only a handful of Hoag-type galaxies exist in the observable universe, Rubin's massive dataset has the potential to reveal them. Euclid, launched by the European Space Agency, will add another dimension, dedicated to mapping dark matter and dark energy. Euclid will survey billions of galaxies across more than 1/3 of the sky. Its sharp images and near-infrared capabilities will be particularly useful for distinguishing ring galaxies from spirals and ellipticals. By looking deeper into the past, Euclid could even uncover whether Hoag-like systems were more common in earlier epochs of galaxy evolution, only to fade as the universe aged. Together, Rubin and Euclid form a complementary pair. Rubin excels in time-domain astronomy, catching transient phenomena and faint structures with repeated visits. Euclid offers unparalleled depth and resolution across cosmic distances. If Hoag's object is truly one of many, these instruments will be the ones to reveal its kin. But what if they find none? What if after cataloguing billions of galaxies only Hoag's object fits the description? The absence of siblings would make the galaxy even more significant, proving that it is not just rare but singular, a structure so improbable it may never be repeated in the observable universe. That too would be a discovery pointing us toward physical conditions so specific they were met only once in cosmic history. Either outcome is thrilling. If we find a population of Hoag-type galaxies, we gain a new class to study new patterns, to model, and new insights into the physics of rings. If we confirm Hoag's uniqueness, we confront a puzzle of staggering improbability. In both cases, the future of galaxy surveys will bring clarity to a mystery that has lingered for nearly a century. For now, Hoag's object remains the lonely jewel of its kind. But the universe is vast, and with Rubin and Euclid, our net has never been wider. Perhaps hidden among the billions of cosmic islands, another perfect ring waits to be discovered. If future surveys like Rubin and Euclid uncover more galaxies that share Hoag's object's strange geometry astronomy, we'll face a new challenge: defining a class. For now, Hoag stands as a singular oddity, a one-off in the cosmic zoo. But science thrives on patterns. Once a handful of similar examples emerge, the instinct will be to connect them, to treat them not as accidents, but as members of a family. This family might be called Hoag-type galaxies, or perhaps detached ring galaxies. Their defining features would be a near-spherical central core, a sharply bounded void, and a luminous ring suspended in perfect symmetry. With multiple specimens, astronomers could compare sizes, ages, star populations, and ring sharpness, searching for common traits. Are their cores always old spheroids? Do their rings always consist of young blue stars? Is the void always empty, or do some contain faint traces of gas? Every answer would add definition to the emerging class. Such a discovery would also shift how we view galactic evolution. At present, spirals and ellipticals dominate our models, with irregulars and collisions providing the rest of the spectrum. Hoag-type galaxies would demand a new evolutionary track, a pathway in which galaxies shed their arms, isolate their cores, and form pristine rings under rare conditions. Whether this process is triggered by collisions, resonance, or dark matter interactions, it would need to be incorporated into the grand narrative of how galaxies grow and change. The implications would ripple outward. A population of Hoag-type galaxies might tell us that the universe is more diverse than our current taxonomy suggests. It would hint that symmetry, often considered fragile in a chaotic cosmos, can emerge more frequently than expected. And it would give us new laboratories for testing physics, since each member of the family would offer a different vantage point on the same fundamental processes. Classification has always been a turning point in astronomy. When spirals and ellipticals were first distinguished, they opened the door to modern galactic science. When quasars were recognized as a separate class, they reshaped our understanding of black holes and active nuclei. If Hoag's object is someday joined by siblings, the act of naming and defining them will mark a similar milestone. The cosmos will have revealed not just a single curiosity, but an entire lineage. Until then, the idea remains hypothetical, but the possibility hangs in the air, sharpened by every new sky survey. That Hoag's object is not a lonely freak of nature, but the brightest jewel of a hidden constellation of kin. Galactic evolution is often described as a continuum. Spirals with their graceful arms and rich supplies of gas are seen as youthful, dynamic systems. Ellipticals, by contrast, are ancient and quiescent, their gas long consumed their stars, drifting in featureless swarms. Yet the precise path from one form to the other is a subject of debate. Do spirals gradually lose their structure through mergers and interactions? Do ellipticals form in sudden, violent collisions? Or is there a sequence of intermediate states we have yet to fully recognize? This is where Hoag-type galaxies could play a transformative role. With their central spheroids resembling ellipticals and their surrounding rings echoing the disks of spirals, they appear to straddle both worlds. Their cores speak of age and stability, while their rings shimmer with the vitality of recent star formation. They are neither fully spiral nor fully elliptical, but something in between, a possible transitional state that evolution passes through on its way from order to silence. If confirmed as a class, Hoag-type galaxies might provide the missing link in this story. Imagine a spiral galaxy stripped of its arms by gravitational tides. Its core settles into an elliptical form, but the material shed in the process gathers into a ring. For a time, perhaps hundreds of millions of years, the system exists in this hybrid form. Neither one thing nor the other. Eventually the ring dissipates, leaving behind only the spheroid. In this picture, Hoag's object is not an accident, but a clue showing us what the bridge between spirals and ellipticals could look like. Alternatively, these galaxies may be more than transitional. They might represent a stable configuration that nature finds under rare but repeatable conditions. If so, then they are not bridges but endpoints, a parallel evolutionary path that produces long-lived ringed spheroids. Either way, their existence forces us to expand the taxonomy of galaxies and reconsider the dynamics of transformation. The implications stretch beyond morphology. If rings like these are powered by inflows of gas, then Hoag-type galaxies reveal that star formation can be sustained even in systems with elliptical-like cores. This challenges the assumption that ellipticals are always dead galaxies. If such inflows are common in certain environments, the line between spiral and elliptical becomes blurred, with hybrid systems maintaining pockets of activity far longer than expected. In this sense, Hoag's object is not just a curiosity, but a candidate for a new category of galactic life cycle. Whether as transitional fossils linking spirals to ellipticals or as rare, stable hybrids, they could redefine how we map the flow of time in the universe's great island cities of stars. One of the great puzzles in cosmic history is understanding how and why galaxies stop making stars. Spirals rich in gas can blaze with new generations for billions of years. Ellipticals, by contrast, are barren. Their gas reservoirs gone, their star formation long since extinguished. What switches galaxies from one mode to the other? The transition is elusive because it unfolds slowly over timescales far beyond human observation. Yet Hoag-type galaxies may offer a frozen glimpse of this very moment, the act of shutting down starbirth. Look at the golden core of Hoag's object. Its stars are old, its gas largely consumed, its spectrum dominated by red light. It has the hallmarks of a system that has already gone quiescent. Around it, however, the brilliant ring blazes with hot blue stars, each only a few million years old. The contrast is stark. A dead heart encircled by youthful fire. If this is not a transition, then what is? Astronomers suspect that the void between core and ring represents the frontier of quenching the zone where star formation has already been extinguished. Gas that might have fueled new stars has either been stripped away, heated until it cannot collapse, or diverted outward into the ring. Whatever the mechanism, the result is clear. The middle ground is silent while the outskirts still burn. The galaxy is quenching from the inside out. This pattern fits broader theories of galactic evolution. Many models suggest that star formation does not end all at once, but retreats gradually, starting at the core and moving outward. Central black holes, stellar winds, or shock heating can shut down star birth in the inner regions, while the outer disk or ring lingers as a last refuge of activity. In Hoag's object, we may be seeing this process at its most dramatic, with the gulf between the core and the ring marking the line of battle between activity and silence. If this interpretation is correct, Hoag's object becomes a Rosetta Stone for quenching. By analysing the ages of stars in the core, the void and the ring astronomers can reconstruct the timeline of its shutdown. How quickly did the middle zone empty out? How long has the core been dead? How recently did the ring ignite? Each answer refines our understanding of how galaxies age and why some lose their spark faster than others. The significance goes beyond one object. If Hoag-type galaxies represent transitional systems, then they are snapshots of the universe's great extinguishing, the gradual fading of star formation that shapes galactic populations across cosmic time. To catch such a moment is rare. To analyse it in detail may be one of the keys to unlocking the life cycle of galaxies. If Hoag's object truly represents a galaxy caught in the act of quenching, then the next step is to ask what force shut down the heart while leaving the outskirts alive. Astronomers recognise several mechanisms that can extinguish star formation, and each may leave a fingerprint inside Hoag's object. The most dramatic candidate is the central supermassive black hole. Nearly every large galaxy harbours one, and when active, these monsters can pour out energy across the electromagnetic spectrum. Jets of plasma, winds of high-energy particles, and intense radiation can heat or expel the gas that might otherwise form stars. In some galaxies, these active galactic nuclei create vast cavities, blowing away star-forming fuel for tens of thousands of light years. If Hoag's core once flared as a quasar or radio source, the energy could have sterilized its interior, leaving the void we see today. The old red stars in the spheroid may be survivors of an era when the black hole reigned, shutting down the core's youth. A gentler but still potent mechanism is stellar feedback. When massive stars explode as supernovae or drive fierce winds during their lifetimes, they inject energy into the surrounding medium. In dense spirals, this can regulate star formation without halting it. But in an environment like Hoag's, feedback could push gas outward, evacuating the inner regions and feeding the ring. Over billions of years, repeated bursts of feedback may have carved out the void, leaving behind an empty zone that even the galaxy's gravity could not refill. Then there is the role of the dark matter halo itself. Simulations suggest that halos can heat gas as it falls inward, shocking it to temperatures so high that it cannot cool and collapse into stars. This process, sometimes called halo quenching, is thought to explain why massive galaxies stop forming stars even when surrounded by gas. In Hoag's object, the halo may have established a thermal barrier around the core, keeping the interior dry, while allowing inflows to settle into the ring. If so, the galaxy is a case study in how dark matter sculpts not just motion, but also star formation. Each mechanism paints a different picture. If the black hole quenched the core, we might find faint X-ray echoes or radio relic signatures of past activity. If stellar winds and supernovae were the culprits, the chemical fingerprints of expelled gas should linger in the ring. If halo quenching dominates, then the temperature and distribution of circumgalactic gas hold the answers. Unravelling which force prevailed in Hoag's object could illuminate the broader mystery of why galaxies across the cosmos go dark. In truth, the answer may be a combination. Quenching is rarely a single stroke, but a symphony of processes layered over billions of years. In Hoag's object, the silence of the core, the emptiness of the void, and the brilliance of the ring may all be chapters in the same story. The long, complex death of star formation written across a galaxy unlike any other. Clues to the true cause of quenching in Hoag's object are scattered across the spectrum, waiting to be pieced together. Each proposed mechanism, a central black hole, stellar feedback, or halo quenching, leaves behind distinct signatures. By hunting for these signals, astronomers hope to reconstruct the hidden history of the galaxy. The first suspect, the central supermassive black hole, can be investigated through high-energy observations. Even long after a quasar phase ends, echoes can remain. X-ray telescopes search for faint hot gas near the core, while radio observatories scan for the remnants of past jets. If Hoag's spheroid once hosted an active nucleus, evidence may linger in the form of cavities, lobes, or spectral lines from gas shocked by ancient outflows. To date, surveys have found Hoag's core to be quiet, with no obvious radio jets or X-ray hotspots. Yet the absence of current activity does not rule out a violent past. The galaxy may bear scars too faint for our instruments to detect, scars that future missions like Athena or Lynx could reveal. Stellar feedback offers subtler traces. If supernovae and winds from massive stars evacuated the inner zones, the expelled material must have gone somewhere. Astronomers therefore analyze the chemical composition of the ring. Elements such as oxygen, carbon, and iron are the fingerprints of past stellar generations. If the ring is enriched beyond what its stars alone could have produced, it suggests that material was blown outward from the core and redeposited in the outskirts. Preliminary spectra hint at elevated metallicity in the ring, but the data are not yet definitive. The case remains open. Halo quenching is trickier to confirm since it operates invisibly through temperature. Gas heated as it falls into the halo remains too hot to collapse, but detecting this requires mapping the circumgalactic medium. Ultraviolet spectroscopy of background quasars can reveal absorption lines from hot diffuse gas surrounding the galaxy. A lack of cold inflows near the core coupled with hot plasma signatures would support the halo quenching scenario. Current data are sparse, but early studies lean toward the idea that Hoag's halo is unusually effective at keeping its interior dry. The interplay between these clues forms the real mystery. The quiet black hole suggests feedback is not active today. The enriched ring hints at past outflows. The halo may still be heating gas, preventing replenishment. Together, the evidence points not to a single cause but to a layered history. An ancient active nucleus that silenced the core stellar winds that pushed gas outward, and a dark halo that sealed the fate by blocking new supplies. Astronomers are still gathering the pieces. Each telescope adds another layer to the puzzle, narrowing the possibilities, and with every new spectrum, Hoag's object transforms from an isolated curiosity into a case study in galactic mortality, a silent witness to the forces that end star formation across the universe. Imagine Hoag's object not as the serene jewel we see today, but as a raging beacon in the distant past. Billions of years ago, its central black hole may have awakened, feeding on torrents of gas spiraling into its maw. As matter fell inward, it heated to extreme temperatures, unleashing torrents of radiation and launching jets of plasma at near-light speed. For a time, the quiet spheroid at the galaxy's heart may have rivaled entire quasars, outshining all its stars combined. If this scenario is true, then the Hoag's object we observe now is the aftermath of that cosmic storm. The energy unleashed during its quasar phase could have been enough to strip the galaxy's inner regions bare. Gas that might have formed stars was either blasted outward, pushed into the outer halo, or heated beyond its ability to collapse. The empty gulf between core and ring becomes not just an architectural oddity, but a scar left by a black hole's fury. This interpretation carries profound implications for galactic evolution. For decades, astronomers have debated the role of black holes in shaping galaxies. Are they passive passengers growing quietly as stars form around them? Or are they architects dictating the fate of entire systems with their violent feedback? If Hoag's object truly bears the mark of a quasar past, the evidence leans toward the latter. Its very structure would testify that black holes can not only quench star formation in a core, but sculpt the morphology of a galaxy on scales of tens of thousands of light years. Detecting proof of such a past is challenging but not impossible. Astronomers search for fossil evidence. Faint X-ray echoes from gas once shocked by jets, radio lobes drifting beyond the spheroid, or unusual metallicity patterns in the ring that betray gas swept outward long ago. Even the precise ages of the stars in the ring could carry clues, for if they all formed in a single burst, it may have been triggered by gas displaced during the black hole's peak activity. If confirmed, Hoag's object would become one of the clearest demonstrations of quasar feedback reshaping a galaxy. It would show that black holes are not only destroyers of star birth but also creators of new patterns, capable of carving voids and igniting rings. The elegant geometry we marvel at today may paradoxically be the product of chaos. This realization reframes the galaxy from anomaly to testimony. Its perfection would not be a quirk of nature, but the legacy of an engine powerful enough to reorder stars on galactic scales. And in that sense, Hoag's object becomes more than a curiosity. It becomes a monument to the power of black holes. Silent now, but echoing with the memory of a quasar that once burned brighter than all its stars combined. If Hoag's object truly carries the scars of a quasar, then the implications stretch beyond a single galaxy. It suggests that ring galaxies themselves may not always be the product of collisions or resonances, but of central black holes imposing their will on their host systems. Could it be that in some cases the most delicate circles of stars in the universe are written by engines of destruction? Other ring galaxies provide tantalizing hints. The Cartwheel Galaxy, famous for its brilliant ring, also hosts evidence of energetic outflows in its core. Several smaller ring galaxies catalogued in deep surveys show weak radioactivity, as though their central black holes have not fully gone silent. Though most astronomers attribute the rings to collisions, the overlap between ring structures and black hole feedback remains difficult to ignore. Hoag's object, with its flawless isolation and emptiness, may simply be the purest example. The mechanism would be straightforward if extreme. A quasar outburst heats and ejects gas from the central regions. Some of this material escapes entirely, but some stalls at a stable orbit farther out where it cools and collapses into stars. Instead of fueling the core, the gas builds a detached ring. In this view, Hoag's object is not a freak accident, but the natural endpoint of a powerful feedback cycle. The core silenced, the middle evacuated, and the outer regions ignited. If true, this changes how we interpret galaxy morphology. Rings would no longer be solely the aftermath of collisions. They would also be the fingerprints of black holes, cosmic signatures left by feedback on galactic scales. And since quasars were far more common in the early universe, it could mean that many galaxies once passed through Hoag-like stages, brief symmetric forms sculpted by nuclear fire, now long faded into ellipticals. Testing this idea will require a systematic search. Astronomers must examine ring galaxies across the spectrum, looking for subtle indicators of past quasar activity. Enriched metallicities in their rings, faint X-ray cavities, or the relic glow of radiolobes. If more cases are found, Hoag's object will cease to be an isolated mystery and become the archetype of a feedback-driven morphology. The connection would be profound. It would mean that black holes do more than shape the fates of stars. They can dictate the very architecture of galaxies. Perfect rings of blue stars glowing like halos may be the monuments left behind by quasars that once lit the universe. And among them, Hoag's object would stand as the clearest, most enduring example of how chaos and symmetry can coexist in cosmic design. The universe we see today is quiet compared to its past. Billions of years ago, when galaxies were young and gas was plentiful, quasars blazed across the cosmos in numbers we can scarcely imagine. At that time, black holes gorged themselves on streams of matter, their outbursts shaping the destinies of their host galaxies. If feedback from these furious engines is truly capable of sculpting rings, then Hoag's object may not be unique at all. It may simply be one of the few survivors of an era when such structures were far more common. In the early universe, conditions were perfect for creating galaxies like Hoag's. Gas was abundant, accretion rates were high, and black holes were hyperactive. Powerful outflows could have cleared central regions, driving matter outward, where it condensed into detached rings. For a brief time, cosmologically speaking, such galaxies may have dotted the skies, glowing with concentric geometry forged by nuclear fire. But time is a relentless eraser. Most of these systems would not survive intact. Their rings would dissolve, their cores merge, their symmetry blur. What remains today may be only the rare fossils, the galaxies whose halos were stable enough to preserve the imprint for billions of years. If this view is correct, Hoag's object is not an anomaly, but a relic, a window into a vanished epoch of galactic evolution. Its symmetry then is not improbable chance but remarkable preservation. It endured while its siblings fell apart, leaving it as the lone messenger from an age when black holes routinely sculpted galaxies into shapes we now struggle to imagine. This perspective aligns with what we know of cosmic history. Quasars peaked around 10 billion years ago, then declined sharply as galaxies ran out of cold gas to feed them. If ring galaxies were tied to that quasar era, their numbers would have dwindled in lockstep. By today, only a handful would remain isolated survivors scattered across the universe. Hoag's object might simply be the one that happened to endure with near-perfect geometry. The search for similar fossils is ongoing. Deep surveys occasionally turn up candidates galaxies with detached rings and quiescent cores. Most, however, lack Hoag's flawless symmetry. Perhaps they are the worn remnants of once pristine structures, their rings faded by time. If so, each imperfect circle is another whisper of the quasar age, another fragment of a story told most clearly by Hoag's object. To view the galaxy this way is to place it in context. It is not an isolated freak, but a survivor of a cosmic era we can no longer witness directly. Its perfect ring is the echo of an epoch when the universe itself was louder, brighter, and more violent. And in the echo lies the key to understanding not only how one galaxy formed, but how billions of others lived and died in the furnace of the young cosmos. To understand the universe we live in now, astronomers often look back to its most chaotic chapters. One of the most dramatic was the quasar epoch, roughly 10 to 11 billion years ago, when supermassive black holes fed with a hunger that defies imagination. Their brilliance lit up the young cosmos, and their feedback reshapes the galaxies around them. Hoag's object, though quiet today, may be one of the best fossils we have to reconstruct that forgotten golden age. During the quasar peak, galaxies were packed with cold gas, the raw material for both stars and black holes. When gas funneled into galactic centers, black holes ignited, blasting out winds and jets, powerful enough to reach tens of thousands of light years. These outflows could quench star formation in the core while simultaneously triggering new bursts at the periphery. In this framework, Hoag's object is not mysterious at all, but the lingering imprint of a process that once played out across the cosmos. Black holes carving voids, then igniting rings of fire. The key lies in timing. By measuring the ages of stars in Hoag's ring, astronomers can estimate when its last great burst of star formation occurred. If that date coincides with the decline of quasar activity in the broader universe, the connection becomes stronger. The galaxy would be not just a curiosity, but a timestamp, a preserved signature of when quasar-driven feedback was at its peak. Its geometry would act like a fossilized ripple frozen in place while most of its contemporaries faded or transformed. This possibility excites cosmologists because direct evidence of the quasar epoch is scarce. We see quasars themselves blazing like cosmic lighthouses in the distant past, but their host galaxies are hard to study, lost in the glare of their nuclei or blurred by distance. Hoag's object, however, offers a clean laboratory. Its black hole is quiet now, its ring luminous but not overwhelming. The chaos has cooled, leaving behind a system that can be studied in detail. Every orbit of its stars, every element in its gas, is a record of forces that once dominated the young universe. If we can decode that record, Hoag's object could help reconstruct the cosmic balance sheet of the quasar era. How much gas was expelled, how much was transformed into stars, how much was locked away in black holes. That balance shaped the galaxies we see today. The fact that the Milky Way is not a ring galaxy may be because its black hole's outbursts were weaker, or its halo less symmetric. By comparing fossils like Hoag's to ordinary spirals and ellipticals, astronomers can piece together the spectrum of outcomes from that violent age. Thus, Hoag's object becomes more than an oddity. It is a portal to the past, a preserved echo of the quasar epoch that built the modern universe. If we learn to read its geometry, we may finally understand how the most violent engines in the cosmos sculpted beauty, symmetry, and silence from chaos. The strangeness of Hoag's object becomes even sharper. When we hold it against the galaxy we know best, the Milky Way. Our home galaxy is a barred spiral with sweeping arms that cradle gas, dust, and star formation, across a disk 100,000 light-years wide. Its structure is busy, asymmetrical, full of clumps and streams. It looks nothing like the perfect symmetry of Hoag's ring, and yet in broad strokes both galaxies are subject to the same laws of physics, the same cosmic ingredients of dark matter, gas and stars. Why then did their fates diverge so dramatically? One key difference is central activity. The Milky Way's supermassive black hole Sagittarius A is quiet. Though it occasionally flares, it has not undergone a sustained quasar phase in billions of years. Without that fury, the galaxy's core has not been scoured clean, nor has its gas been pushed into detached rings. Star formation continues across its spiral arms, a steady rhythm unbroken by catastrophic feedback. Hoag's object, by contrast, may bear the scars of a much more violent nucleus, one capable of rearranging its entire architecture. Another distinction lies in environment. The Milky Way belongs to a small group of galaxies gravitationally bound with Andromeda Triangulum and dozens of dwarfs. Interactions within this group have stirred our galaxy's outskirts, pulling streams of stars and gas into long tidal tails. Hoag's object, by comparison, is remarkably isolated with no major companions nearby. Its symmetry may owe as much to its solitude as to its internal dynamics. Left alone, it could evolve without the distortions of neighbours allowing its perfect ring to persist. Even Andromeda, the nearest giant to us, offers an instructive contrast. It is a spiral like the Milky Way, but more massive, with a turbulent history of mergers. Streams of stars arc across its halo, evidence of smaller galaxies swallowed over time. Andromeda's black hole is larger than ours, yet it too is relatively dormant. The local group as a whole shows no sign of galaxies shaped like Hoag's. This absence suggests that whatever forces produced Hoag's object were rare, tied to specific conditions not met in our corner of the cosmos. The comparison underscores how contingent galactic evolution is. A small change in black hole activity, a difference in halo symmetry, a quirk of environment, and the Milky Way might look profoundly different. Instead of spirals, we might orbit within a luminous ring. Our night sky dominated by an arc of young stars encircling a golden spheroid. The fact that we do not is a reminder that cosmic history is full of branching paths, many of which end in structures as strange and improbable as Hoag's object. For astronomers, this comparison is not just philosophical. By studying the differences between Hoag's object and galaxies like the Milky Way, they can isolate the variables that matter most, which factors shape morphology, which preserve symmetry and which destroy it. Each contrast sharpens the role of black holes, halos and environment in guiding galactic destiny. It is tempting to imagine what the Milky Way might have looked like billions of years ago. Today it is a barred spiral, its disk full of winding arms and bright nebulae. But galaxies are not static. Their shapes are snapshots in an endless evolution. Could our own galaxy once have worn a ring, perhaps even resembling Hoag's object, only to lose it as time marched on? And if so, what traces of that ancient phase might still linger in its stars? Some astronomers have looked for subtle clues in the distribution of stellar populations across the Milky Way. Rings do exist in our galaxy, not perfect detached circles, but structures like the Monoceros ring and the more diffuse outer ring, both spanning tens of thousands of light years. These arcs of stars could be remnants of past events, tidal streams from devoured dwarfs or displaced gas collapsing into curved orbits. While they lack the purity of Hoag's perfect circle, they hint that ring-like structures are not alien to the Milky Way's history. Our central bulge also carries whispers of transformation. It is boxy and irregular, unlike the pristine spheroid of Hoag's object, but simulations suggest bulges can evolve dramatically over time. A more quiescent spheroid-like core might once have existed, later reshaped by bar instabilities and spiral arm dynamics. If the Milky Way ever had a cleaner separation between core and disk, it could have resembled a Hoag-like state before its present complexity emerged. Gas dynamics offer another line of evidence. The Milky Way's halo contains streams of hydrogen that extend far beyond the visible disk. Some of these flows are ancient leftovers from interactions or infall billions of years ago. If a quasar phase once blasted gas outward, traces could remain in these extended reservoirs. Detecting them is challenging, but their presence raises the possibility that the galaxy has undergone episodes of feedback intense enough to sculpt large-scale structures. Of course, the Milky Way's crowded environment complicates the picture. Interactions with satellites, especially the Sagittarius dwarf galaxy, have pulled and stirred its disk for eons. Such disruptions would erase any fragile symmetric ring long ago. Even if we once looked like Hoag's object, the relentless dance of companions would have blurred the evidence, leaving only irregular fragments in the outskirts. Still, the question lingers. Could the Milky Way have passed through a transitional stage resembling Hoag's object? Perhaps. If it did, the proof may lie in the ages of stars in its outer rings, in the chemistry of its halo gas, or in the faint ripples of structure that large-scale surveys are only now uncovering. The Gaia mission, with its precise maps of billions of stars, is already revealing patterns once invisible. Somewhere in that data, hidden among the spirals and streams, could be the fossilized echoes of a geometry long since lost. Every galaxy is both a city of stars and a factory of elements. Within their hearts, nuclear fusion forges the heavy atoms that make planets, oceans, and life possible. Yet galaxies do not keep these elements to themselves. They distribute them outward, enriching the vast intergalactic medium. The question is, which galaxies were most efficient at spreading these metals in the early universe? If Hoag-type galaxies were once more common, they may have been key players in seeding the cosmos. The mechanism lies in their geometry. A quasar-driven outburst or massive feedback cycle could blast gas outward, evacuating the core and depositing it in the outer ring. That expelled gas-rich and heavy elements from supernovae and stellar winds would either form new stars in the ring or continue its journey into intergalactic space. In this way, galaxies like Hoag's object could act as giant sprinklers, scattering metals across regions far larger than their visible boundaries. Evidence supports this idea. The ring of Hoag's object is unusually enriched with metals more than expected for its population of stars alone. This suggests that processed material from the core was expelled outward, carrying the fingerprints of multiple stellar generations. The void in turn may represent the region cleared by that expulsion. If gas also escaped entirely, it would have flowed into the cosmic web, joining the reservoirs that feed future galaxies. This has profound implications for the early universe. Quasars were common 10 billion years ago, and if many galaxies looked like Hoag's during that epoch, their collective feedback could explain the widespread enrichment of intergalactic gas observed today. Even distant low-density regions show traces of carbon, oxygen, and iron elements that must have been carried there somehow. Hoag-type events provide a plausible mechanism: black holes ejecting fuel galaxies, sculpting rings, and metals flying outward into the void. Simulations suggest that without such processes, the cosmic web would be far poorer in heavy elements. Star formation in isolated galaxies alone cannot explain the chemical fingerprints we see in intergalactic space. But if feedback-driven ring galaxies were once a common phase, the puzzle fits together. They were not just rare curiosities, but engines of cosmic chemistry spreading the seeds of complexity into the young universe. If so, then Hoag's object today is more than a fossil of morphology. It is a relic of cosmic ecology. Its structure tells a story not only of stars and dark matter, but of how the universe became enriched enough to form planets, atmospheres, and life. In its luminous ring and hollow core, we may glimpse the very processes that allowed our own world to exist. Galaxies do not evolve in isolation. Each one is both a consumer and a contributor, drawing gas from the cosmic web while also feeding enriched material back into it. If Hoag-type galaxies were once more common, their violent feedback cycles could have shaped not just their own destinies, but the destinies of galaxies yet to form. In this sense, they may have acted as architects of the next generation of cosmic structures. Consider the role of metals. In the earliest galaxies, stars were made almost entirely of hydrogen and helium, the primordial elements forged in the Big Bang. Without heavier atoms, cooling was inefficient and star formation proceeded slowly. But once metals entered the mix, gas clouds could radiate away heat, more effectively collapsing into stars at a faster rate. If Hoag-like systems ejected huge volumes of metal-rich gas into intergalactic space, they may have accelerated this process across the cosmos. Galaxies forming later would inherit richer material building stars more efficiently than their predecessors. This could explain why galaxies just a few billion years after the Big Bang already show surprising levels of chemical enrichment. Observations of quasars and distant galaxies reveal strong signatures of elements like carbon and oxygen far earlier than models once predicted. The missing ingredient may be galaxies like Hoag's object, transitional forms that blasted metals outward, spreading them quickly across vast regions. In effect, they could have been catalysts priming the universe for a faster pace of evolution. The impact might extend to structure as well. Gas expelled into halos or rings could serve as reservoirs for later accretion. Neighbouring galaxies might sweep up this material, altering their growth trajectories. Even galaxy clusters may have been influenced as expelled matter enriched the intracluster medium, changing the balance of cooling and heating in the largest structures of all. Seen in this light, Hoag-type galaxies are not marginal curiosities. They are potential pivot points in cosmic history, playing a role far larger than their numbers suggest. Their feedback cycles may have turned the early universe from a chemically simple place into one ready to support the diversity of galaxies we see today. Without them, spirals like the Milky Way might have taken longer to form their stars poorer in metals, their disks less efficient at generating complexity. If this is true, then studying Hoag's object is not just about understanding one rare system. It is about tracing the fingerprints of a process that shaped the chemical and structural foundations of the universe itself. A single galaxy becomes a witness to the grand chain of inheritance, where each generation leaves its mark on the next. And in Hoag's perfect ring, glowing with the metals of countless past stars, we may see the evidence of that inheritance written in light. The universe keeps records, and not all of them are written in starlight. Some are etched in chemistry in the ratios of elements that flow through galaxies and scatter across the intergalactic medium. If Hoag-type galaxies truly acted as engines of enrichment, then their legacy should still be detectable today, not only in their rare surviving forms, but in the chemical fingerprints imprinted across space. Astronomers study this cosmic chemistry through spectroscopy. When light from distant quasars passes through intergalactic gas, it carries with it the absorption lines of the elements in that gas. By analysing these lines, we can reconstruct the composition of regions billions of light years away. Surprisingly, even low-density voids far from galaxies contain traces of carbon, oxygen, and silicon. This enrichment is difficult to explain unless metals were dispersed on truly colossal scales. Hoag-like feedback events ejecting gas tens of thousands of light-years outward provide one of the most compelling mechanisms for spreading those elements so widely. Stars too carry the record of past enrichment. Populations of stars and galaxies across the universe show distinct metallicities, the proportion of matter made of elements heavier than helium. If Hoag-type galaxies expelled their metals into surrounding space, then subsequent generations of stars forming in neighbouring systems would inherit that material. In this way, the chemistry of one galaxy becomes the inheritance of another. Even in the Milky Way, stellar populations with unusual metal ratios may reflect enrichment not from our own history, but from ancient neighbours long gone. One particularly telling signature would be overabundances of certain elements relative to others. If quasar-driven outflows preferentially expelled supernova products such as oxygen and iron, then regions touched by such events should show distinctive ratios compared to areas enriched only by steady stellar winds. Detecting such patterns across intergalactic space could be indirect evidence of Hoag-like episodes. In effect, the chemistry of the cosmos becomes a forensic tool pointing back to rare structures that reshape their surroundings. The challenge is sensitivity. These signals are faint, often buried in the noise of distant light. Yet new instruments are beginning to make the impossible possible. Telescopes like the extremely large telescope in Chile with its vast mirror and high-resolution spectrographs will allow astronomers to measure elemental abundances with unprecedented precision. By cross-matching these chemical maps with galaxy surveys, they may be able to trace which regions were enriched by ordinary spirals and which by extraordinary Hoag-like events. If successful, this approach will reveal Hoag's object not as an isolated oddity, but as part of a larger story written in chemistry across the cosmos. Even if its siblings have long since faded, their fingerprints may still lace the intergalactic medium, whispering of a time when galaxies carved rings of fire and seeded the universe with the metals of creation. Hoag's object began as a curiosity, a strange ring of stars in a lonely corner of the sky. But as we have followed its story, piece by piece it has grown into something far greater. It is no longer just a galaxy with an unusual shape. It is a relic of cosmic violence, a fossil of the quasar age, a monument to the power of black holes to sculpt the very architecture of the universe. Its ring may hold the chemistry of past explosions. Its void may be the scar of a black hole's fury. Its symmetry may be the improbable survival of a form once common, now almost erased. Hoag's object reminds us that galaxies are not frozen. They are shaped broken and rebuilt by forces we can scarcely control. In its glowing ring we see not only the light of stars but the echo of a time when the cosmos itself was louder, brighter, and more alive. And perhaps most important of all, it reminds us that we are connected to this story. The metals in our blood, the oxygen, we breathe, the calcium in our bones, they may have been flung into space by galaxies like Hoag's in their violent youth. Without those ancient outbursts, the universe might still be a place of only hydrogen and helium, too simple for planets, oceans, or mines to form. When you look at Hoag's object, you're not just looking at a ring of stars. You're looking at a time machine, a relic of how galaxies lived, died, and gave birth to the universe we inhabit. It is a question carved in starlight. How many more stories like this remain hidden, waiting for us to uncover? The answer lies in the skies still unexplored in the galaxies yet to be mapped, and in the chemistry of the cosmos itself. Hoag's object is just the beginning. The cosmos is vast and its mysteries are endless. Tonight we have journeyed into the heart of one of its strangest wonders, a galaxy that defies symmetry and whispers of forgotten ages. Hoag's object is more than light on a telescope's mirror. It is a question suspended in space, a reminder that the universe still holds secrets too great for us to ignore. As we close this chapter, look up and remember, every star overhead, every spiral in the deep sky carries a story as rich and surprising as Hoag's. Some may speak of creation, others of destruction. All are threads in the same cosmic tapestry. Thank you for joining this journey across time and distance. Stay curious, because the next mystery is already waiting in the stars.